Hello there and welcome back to the Science Sleepy Minds. Tonight, picture yourself standing in a tunnel 17 miles long, buried 100 metres beneath the French-Swiss border. The air hums with a barely audible whine of superconducting magnets chilled to temperatures colder than outer space. Somewhere in that ring of steel and silence, a handful of atoms made entirely of antimatter are floating inside a magnetic bottle, and they just did something that, according to every physics textbook you've ever skimmed or pretended to skim, should be flatly impossible. We are talking about a discovery so strange that the scientists who made it double-checked their instruments, triple-checked their math, and then apparently sat in stunned silence for a while before telling anyone. You're about to spend the next little while learning exactly what they found, why it matters, and why it could quietly rewrite the rules of the universe. Fair warning, the topic is so deep, so layered, and so deliciously weird that you probably will not survive this one with your eyes open. That is, after all, the whole point. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And while you're at it, drop a comment with your location and your local time. I always love seeing who is tuning in from Tokyo at 3 in the morning versus someone in Buenos Aires settling in after dinner. It makes this whole thing feel like a worldwide sleepover, which, honestly, it kind of is. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You begin, as all good stories about the edge of physics do, underground. Not metaphorically underground, not figuratively underground, but literally encased in rock and concrete on the outskirts of Geneva, Switzerland. The European Organisation for Nuclear Research, better known by its French acronym CERN, operates the largest and most complex experimental facility ever constructed by human beings. When people hear the name CERN, they usually think of the Large Hadron Collider, that famous ring where protons are smashed together at nearly the speed of light. And yes, that machine is here, and yes, it is spectacular, but tonight you're not visiting the collider. Tonight you're walking past it, deeper into the complex toward a quieter, stranger corner of the laboratory, where a much smaller experiment is asking a much bigger question. The facility you're approaching is called Alpha. It does not smash anything. It does the opposite. It catches tiny pieces of antimatter, the rarest and most volatile substance in the known universe, and holds them perfectly still so scientists can study them with lasers. If that sounds like science fiction, you are not wrong to feel that way. As recently as the 1990s, trapping a single atom of antimatter was considered a pipe dream. The stuff annihilates the instant it touches ordinary matter. One atom of antihydrogen grazing the wall of its container releases a flash of energy and ceases to exist. Keeping it alive long enough to measure it is like trying to hold a soap bubble in a room full of needles. Yet here, in this hall, they have done it. They have trapped antihydrogen atoms for minutes at a time, poked them with precisely tuned laser light, and read the faint glow that comes back. And in doing so, they have stumbled onto a result that has sent a quiet ripple of panic through the theoretical physics community. Now, you might be wondering what antimatter even is, and that is a perfectly reasonable question considering that most people go their entire lives without encountering a single atom of the stuff. In the simplest terms, antimatter is a mirror image of ordinary matter. Every particle that makes up your body, every electron zipping around your atoms, every proton sitting in your nuclei, has a corresponding antiparticle with the same mass but opposite charge. An electron carries a negative charge, so its antimatter twin, the positron, carries a positive charge. A proton is positive, so an antiproton is negative. When a particle meets its antiparticle, they do not shake hands. They annihilate each other in a burst of pure energy, the most efficient energy conversion process in the universe, making even nuclear fusion look sluggish by comparison. This concept alone is wild enough, but the real puzzle is what happened at the beginning of time. When the Big Bang ignited roughly 13.8 billion years ago, the laws of physics as we understand them say it should have produced exactly equal amounts of matter and antimatter, and those equal amounts should have promptly found each other, annihilated completely, and left behind nothing but a sea of radiation. No stars, no planets, no cozy beds, no you. Yet here you are, made entirely of matter, lying in a universe that is overwhelmingly made of matter, with antimatter almost nowhere to be found in nature. Something, at some point, tipped the balance. Something broke the symmetry. Physicists have been hunting for that something for decades, and CERN's alpha experiment may have just caught its shadow. The specific result, which we will unpack in gorgeous detail as the night goes on, involves a measurement of antihydrogen, the simplest antimatter atom, made of one antiproton and one positron. Scientists compared the way antihydrogen absorbs and emits light to the way ordinary hydrogen does the same thing. According to a principle called CPT symmetry, the deepest symmetry in all of physics, those two measurements should be identical, not close, not almost, not within a reasonable margin. Identical. Scholars still argue whether CPT symmetry is truly fundamental or merely an emergent property of deeper laws we have not found yet, and that debate has been simmering politely in lecture halls for years. But this new data suggests the measurements are not identical. There is a discrepancy, tiny but persistent, lurking in the spectral lines of antihydrogen. And if that discrepancy holds up, it means the universe's most sacred mirror has a crack in it. You do not need to understand quantum field theory to feel the weight of that. Imagine discovering that your reflection in a mirror blinked when you did not. That is the vibe. That is the quiet, creeping strangeness that has physicists refreshing their inboxes and booking last-minute flights to Geneva. The year is 2025, and the impossible just became a data point. So settle in. Pull that blanket up a little higher. You and the universe have a lot to talk about tonight. The story of antimatter does not begin in a tunnel under Geneva. It begins, as so many revolutionary ideas do, with a single person staring at an equation and realizing it contains something terrifying. The year is 1928, and the person is Paul Dirac, a British theoretical physicist so quiet and socially awkward that his colleagues at Cambridge invented a unit of measurement called the Dirac, defined as 1 word per hour. Dirac was not much for small talk, but he was extraordinarily gifted at listening to mathematics, and in 1928 the mathematics was screaming. You have to understand where physics stood at that moment. Quantum mechanics was brand new, barely a toddler. Schrödinger had published his wave equation just 2 years earlier. Heisenberg had introduced his uncertainty principle the year before. Einstein's special relativity, meanwhile, was over 2 decades old and thoroughly confirmed. The problem was that nobody had managed to marry these two frameworks together. Quantum mechanics described the behavior of tiny particles beautifully, but it ignored the fact that those particles could move at speeds approaching the speed of light. Special relativity handled high speeds just fine, but it had not been woven into the quantum fabric. Two gorgeous theories sitting in separate rooms, refusing to speak to each other. Dirac decided to introduce them. What he produced was a single equation, now called the Dirac equation, and it was breathtakingly elegant. It described the behavior of electrons in a way that was fully compatible with both quantum mechanics and special relativity. It predicted the electron's spin, a property that had been observed but never explained from first principles. It was, by every reasonable standard, a triumph. But the equation had a quirk. Actually, quirk is too gentle a word. The equation had a bomb hidden inside it. When Dirac solved his equation, he found that it allowed for two kinds of solutions. One described ordinary electrons with negative charge and positive energy, exactly as expected. The other described something with positive charge and, depending on how you interpreted the math, negative energy. That second solution was not supposed to be there. It was like opening your recipe book to make toast and finding detailed instructions for summoning a demon on the facing page. Dirac initially tried to explain away the negative energy solutions. He proposed something called the Dirac sea, a theoretical model in which every negative energy state in the universe was already filled with electrons, and a hole in that sea would behave like a positive particle. He even suggested cautiously that the hole might be a proton, since protons were the only known positively charged particles at the time. Other physicists politely pointed out that this made no sense, because the hole would need to have the same mass as the electron, and protons are nearly 2,000 times heavier. Dirac eventually conceded the point, and, with what you might imagine as a very quiet sigh, predicted the existence of a completely new particle. It would have the same mass as the electron, the opposite charge, and no one had ever seen it before. He called it the anti-electron. The world would later call it the positron. Now here is the thing that makes this moment so remarkable. Dirac did not discover the positron in a laboratory. He discovered it in a notebook. Pure mathematics told him the particle had to exist before any experiment confirmed it. Scholars still argue whether this represents the greatest triumph of theoretical physics or an almost unreasonable stroke of luck, since the Dirac sea model that led to the prediction was, frankly, kind of a mess. Either way, the prediction was out there, floating in the academic ether, waiting for someone to catch the real thing. You might be lying there thinking that antimatter sounds exotic and rare, something that belongs exclusively in particle accelerators and science fiction novels. And in a sense you are right, because antimatter is absurdly scarce in the universe around you. But here is a quirky little tidbit to unsettle your pillow. Your own body produces antimatter. Right now, as you lie there, the potassium-40 isotopes naturally present in your muscles, and bones occasionally undergo a type of radioactive decay called beta plus decay, which releases a positron. Your body emits roughly 5,000 positrons per day. Each one travels less than a millimeter before it bumps into an ordinary electron, annihilates, and produces a pair of gamma rays. You are, at this very moment, a tiny antimatter engine running in the background, and you have never once noticed. It is like finding out your car has a jet turbine hidden under the back seat that fires briefly every few seconds, but never does anything useful. This quirk of biology, by the way, is not just a fun fact for sleepy listeners, it is the entire basis of PET scans, positron emission tomography, one of the most important medical imaging tools in modern hospitals. Doctors inject you with a radioactive tracer that emits positrons. Those positrons annihilate with electrons in your tissue, producing gamma rays that detectors pick up to build a three-dimensional image of what is happening inside your body. So antimatter is not merely an abstract concept in a theorist's equation. It is a diagnostic tool your doctor uses to find tumours. It is practical, life-saving, and happening in hospitals around the world every single day. But back in 1928, none of that existed yet. What existed was an equation, a shy man in Cambridge, and a prediction that the universe contained a mirror version of everything. The next step was for someone to actually find the mirror, and that someone was about to have a very good day in Pasadena, California, armed with nothing more than a magnet, a cloud chamber, and an open mind. You can almost feel the anticipation building, the way the air tightens before a thunderstorm, because what happened next would crack open an entirely new wing of reality. You're still just at the threshold, barely a step inside the door, and already the ground beneath you is shifting. The year's 1932 and you find yourself on the rooftop of a building at the California Institute of Technology in Pasadena. The sun is blazing, the air smells like eucalyptus and ambition, and a young physicist named Carl Anderson is hunched over a device that looks like something a steampunk enthusiast might build in a garage. It is called a cloud chamber, and its design is beautifully simple. You take a sealed container, fill it with supersaturated vapor, usually alcohol or water, and wait. When a charged particle zips through the vapor, it ionizes the gas molecules along its path, and those ions act as seeds for tiny droplets. The particle leaves a visible trail, a ghostly white streak hanging in the mist like a miniature contrail. By placing the whole apparatus inside a strong magnetic field, you can make those trails curve. Positively charged particles curve one way. Negatively charged particles curve the other. The tighter the curve, the lighter the particle. It is, in essence, a photograph of the invisible, and Anderson was very good at reading those photographs. Anderson was not specifically looking for antimatter. He was studying cosmic rays, those high-energy particles that constantly rain down on Earth from deep space. Cosmic rays had been discovered about 2 decades earlier by Victor Hess, who confirmed their existence by hauling radiation detectors up in a hot air balloon, because early 20th century physics was essentially a series of increasingly dangerous field trips. Anderson's job was to catalogue the particles that cosmic rays produced when they slammed into the atmosphere, and on an August afternoon in 1932, he saw something in his cloud chamber that made him stop and stare. There was a track. It curved the wrong way. The curvature told him the particle was positively charged, but the radius of the curve told him the particle was far too light to be a proton. It had, in fact, almost exactly the mass of an electron, a positively charged electron. Anderson had caught Dirac's ghost. He had photographed the positron. You might think the physics community erupted in celebration, but the reality was messier. Many physicists were skeptical. Some thought Anderson had simply misread the direction of the particle's travel, which would flip the apparent charge. Anderson, to his credit, had anticipated this objection. He had placed a lead plate across the middle of his cloud chamber, so he could see the particle lose energy as it passed through, which told him unambiguously which direction it was moving. The track was clear. The charge was positive. The mass was electronic. There was no wiggle room. Within months, other laboratories confirmed the result, and the positron became the first known antiparticle. Anderson received the Nobel Prize in Physics in 1936, sharing it with Hess, the balloon enthusiast who had discovered cosmic rays in the first place. Here is where it gets interesting in a way that speaks to how science actually works behind the polished stories. Anderson later admitted that he was not aware of Dirac's prediction when he made his discovery. He found the positron experimentally, through careful observation, without any theoretical roadmap. Dirac had predicted it mathematically 4 years earlier, but the two threads of discovery were essentially independent. This is one of those moments that scholars still argue about because it raises a genuinely fascinating question about the relationship between theory and experiment. Did Dirac's equation predict the positron, or did it merely accommodate it after the fact? Some historians of science contend that Dirac himself was so confused by the negative energy solutions that his original interpretation, the business about holes in the Dirac sea and protons, was essentially wrong, and that the correct interpretation only became clear after Anderson's discovery forced everyone to take the math seriously. Others maintain that the prediction was genuine, and that Dirac deserves full credit for one of the most extraordinary leaps of theoretical intuition in the history of science. The truth, as usual, is probably somewhere in the middle, tangled up in personality, timing, and the messy way breakthroughs actually happen. What nobody argued about was the implication. If the electron had an antiparticle, did every particle have one? The answer, which would take another couple of decades to confirm fully, turned out to be yes. In 1955, physicists at the University of California, Berkeley, produced the antiproton using the Bevatron accelerator, a machine specifically designed to reach the energy threshold needed to create proton-antiproton pairs. A year later, the antineutron followed. By the early 1960s, the pattern was unmistakable. Every particle in nature had a mirror twin with opposite charge and identical mass. The universe was not just made of matter, it had a complete shadow cast, a parallel set of building blocks that could, in principle, assemble into anti-atoms, anti-molecules, anti-planets, anti-you. A quirky detail worth savouring as you settle deeper into your pillow. When the antiproton was discovered at Berkeley, the press coverage was remarkably calm. The New York Times ran the story, but it did not make the front page. Antimatter, it seems, was considered less newsworthy than the latest political scandal, which is either a commentary on public priorities or evidence that newspaper editors in the 1950s had absolutely no idea what they were looking at. Imagine a parallel universe where that headline ran above the fold and antimatter became a household word 30 years earlier. The history of science funding might look very different, but you are not in that parallel universe. You're in this one lying comfortably in the dark, and the trail Anderson photographed in 1932 has led you to a much deeper question. If matter and antimatter are perfect mirror images, if every property lines up except the sign of the charge, then the Big Bang should have produced them in exactly equal quantities. And equal quantities of matter and antimatter do not coexist. They destroy each other, completely and efficiently, leaving nothing behind but light. The universe, in other words, should be empty. It should be a featureless bath of radiation with no structure, no stars, no planets, and certainly no you wondering about it at this hour. Something went wrong, or rather something went beautifully, inexplicably right, and nobody knows exactly what it was. That mystery is pulling you forward now, deeper into the tunnel, closer to the machines that might finally have an answer. So here you are, existing. Breathing in, breathing out, your chest rising and falling in the dark, and according to the most fundamental equations in physics, none of this should be happening. That is not hyperbole. That is not a poet being dramatic. That is the cold, mathematical consensus of nearly every cosmologist alive. The universe, as best we can calculate, should be empty. Let yourself sink into that thought for a moment, because it is genuinely one of the strangest facts in all of science. Roughly 13.8 billion years ago, the Big Bang erupted from an unimaginably hot, dense state and began expanding. In the first fractions of a second, the energy of that primordial fireball was so extreme that it spontaneously produced particles and antiparticles in enormous quantities. Electrons and positrons, quarks and antiquarks, neutrinos and antineutrinos, all fizzing into existence like champagne bubbles in a bottle that had been shaken by the hand of creation itself. And for every particle that appeared, an antiparticle appeared alongside it. The ledger was balanced, the books were clean. Matter and antimatter born in perfect pairs, filling the infant universe in exactly equal measure. Now, you already know what happens when matter meets antimatter. They annihilate. They convert their combined mass entirely into energy, specifically into photons, and they do so with a thoroughness that would make even the most obsessive accountant weep with admiration. So as the universe expanded and cooled, those particles and antiparticles found each other and destroyed each other, pair by pair, filling the cosmos with a blinding fog of radiation. This process, called pair annihilation, should have consumed everything. Every last electron should have met a positron. Every last quark should have embraced an antiquark. The result should have been a universe containing nothing but photons, a vast structureless ocean of light with no matter and no antimatter whatsoever. And yet, here you are. Here are stars. Here are galaxies. Here is a planet with oceans and mountains and a person lying in bed listening to a video about physics. Something, somewhere in the first moments of existence, produced a tiny surplus of matter over antimatter. The numbers are staggering in their precision. For every billion antimatter particles produced in the Big Bang, there were roughly 1,000,000,001 matter particles. That is it. One extra particle per billion. A rounding error in the cosmic ledger. And when the Great Annihilation swept through, those 1 in a billion survivors were all that remained. Every atom in your body, every star you have ever seen, every grain of sand on every beach on Earth, all of it descended from that impossibly slim surplus. You are, quite literally, a leftover. The universe tipped its scales by 1 part in a billion, and you are what spilled over. Physicists have a name for this imbalance. They call it baryogenesis, which sounds like the title of an experimental jazz album, but actually refers to the process by which the universe ended up with more baryons, meaning protons and neutrons, than antibaryons. The term was formalized in the 1960s and 70s as cosmologists began to take the matter-antimatter asymmetry seriously, and it remains one of the great unsolved problems in physics. In 1967, the Russian physicist Andrei Sakharov, who is perhaps better known for his later work as a human rights activist and dissident, outlined 3 conditions that any successful theory of baryogenesis must satisfy. These are now called the Sakharov conditions, and they are elegant in their simplicity. First, there must exist processes that violate baryon number conservation, meaning reactions where the total number of baryons can change. Second, there must be violations of certain symmetries called C-symmetry and CP-symmetry, which we will get into shortly. Third, these processes must occur out of thermal equilibrium, meaning the universe cannot be in a perfectly balanced state when they happen. Sakharov laid down these rules decades ago, and physicists have been trying to satisfy all 3 simultaneously within known physics ever since. Scholars still argue whether the standard model of particle physics, our best catalogue of all known particles and forces, can generate enough asymmetry to explain the observed surplus. The short answer appears to be no. The standard model contains mechanisms that satisfy each of Sakharov's conditions individually, but when you run the numbers, the amount of asymmetry it produces is laughably small, off by roughly 10 orders of magnitude from what is needed. It is like trying to explain the existence of the Pacific Ocean by pointing to a dripping faucet. The faucet exists and it does drip, but it is nowhere near sufficient. This is why the discovery at CERN matters so much, and why you can feel the narrative tightening around you, like a blanket being tucked in. If the standard model cannot explain why you exist, then something beyond the standard model must be responsible. New physics, unknown particles, undiscovered forces, hidden asymmetries lurking in the fabric of reality itself. And the best place to look for those hidden asymmetries is in the one substance that should be the perfect mirror of matter but maybe, just maybe, is not. Here is a fringe little detail that cosmologists like to whisper about at conferences after the 3rd glass of wine. Some theorists have proposed that the matter-antimatter asymmetry is not universal. They suggest that vast regions of the cosmos might be made entirely of antimatter, separated from our matter-dominated neighbourhood by immense voids. If an antimatter galaxy existed somewhere out there, it would look identical to a matter galaxy through a telescope because the light it emitted would be indistinguishable from ordinary light. The only way to tell the difference would be to look for the gamma-ray signatures produced at the boundaries where matter and antimatter regions met and annihilated. Satellites have searched for those signatures and found nothing conclusive, which most physicists take as evidence that antimatter domains, if they exist at all, must be incredibly far away. But the idea has never been fully ruled out, and it lingers like a strange dream you cannot quite shake. You let that thought settle over you. Somewhere out there, perhaps unimaginably distant, there might be an anti-you made of positrons and antiprotons, lying in an anti-bed, wondering why the anti-universe is made of antimatter. Or perhaps not. Perhaps the asymmetry is absolute, baked into the laws of physics themselves, and the answer lies not in distant galaxies but in the spectral lines of a few hundred antihydrogen atoms floating in a magnetic trap beneath the Swiss countryside. The first real crack in the mirror appeared not at CERN but at a laboratory on Long Island, New York, in the summer of 1964. You're there now, or at least you can imagine yourself there, standing inside Brookhaven National Laboratory, where two physicists named James Cronin and Val Fitch are about to accidentally reshape our understanding of the universe. They were not looking for a revolution. They were running what they considered a fairly routine experiment involving particles called kaons, and what they found was anything but routine. To understand what Cronin and Fitch discovered, you need to get comfortable with the idea of symmetry, which in physics means something slightly different than it does in everyday life. When you look in a mirror, your reflection is symmetric. Left becomes right, right becomes left, but the overall picture is recognizable. Physicists formalize this idea into specific symmetry operations. There are three big ones that matter for tonight's story. The first is called symmetry, which stands for charge conjugation. This operation swaps every particle for its antiparticle. Every electron becomes a positron. Every proton becomes an antiproton. The second is p-symmetry, which stands for parity. This operation flips the spatial coordinates, essentially creating a mirror image of the entire experiment. Imagine reflecting everything through a looking glass so that left-handed processes become right-handed. The third is t-symmetry, which stands for time reversal. This operation runs the experiment backward, like rewinding a film. For a long time, physicists believed that each of these symmetries was individually sacred. If you took any physical process, swapped all the charges, or flipped the mirror, or ran the clock backward, the resulting process should also be a valid physical process. Nature, it was assumed, did not play favourites. The laws of physics were supposed to look the same regardless of how you transform the frame. Then, in 1956, two theoretical physicists named Tsung-Dao Lee and Chen-Ning Yang proposed that one of these symmetries might actually be violated. Specifically, they suggested that the weak nuclear force, the force responsible for certain types of radioactive decay, might not respect parity symmetry. This was a bold and deeply unsettling idea. It meant that nature could, in principle, distinguish between left and right. An experimentalist named Qianxiong Wu tested the hypothesis using cobalt-60 atoms cooled to near absolute zero, and she found that Li and Yang were correct. The weak force violated parity. Nature was, at a fundamental level, left-handed. Wu's experiment was a triumph, though scholars still argue about the fact that she didn't share the Nobel Prize that Li and Yang received in 1957, a snub that many historians of science consider one of the most egregious oversights in Nobel history. But here is where things get sneaky. When parity fell, physicists quickly consoled themselves by proposing that the combined symmetry of C and P together, called CP symmetry, was still preserved. If you simultaneously swapped all particles for antiparticles and flipped the mirror, the resulting process should still obey the same laws. It was a reasonable assumption, a kind of safety net. If nature cheated on the mirror alone, at least it was honest when you combined the mirror with the charge swap. CP symmetry became the new bedrock, and that is exactly what Cronin and Fitch shattered. Their experiment involved neutral kaons, particles made of a quark and an antiquark bound together by the strong nuclear force. Neutral kaons come in two varieties that physicists creatively named K long and K short, based on how long they take to decay. K-short decays quickly into 2 pions. K-long decays more slowly into 3 pions. The key point is that these 2 decay modes have different CP properties. If CP symmetry were perfect, K-long should never decay into 2 pions. It was forbidden, prohibited. Written in bold on the chalkboard with 3 underlines, Cronin and Fitch watched K-long decay into 2 pions. Not often, not dramatically. About 2 times in every 1,000 decays, K-long did the thing it was not supposed to do. A tiny fraction. A whisper of violation. But it was real, it was repeatable, and it meant that CP symmetry was broken. Nature did not just distinguish between left and right. It also distinguished ever so slightly between matter and antimatter. The mirror, even when combined with a charge swap, was imperfect. The discovery earned Cronin and Fitch the Nobel Prize in Physics in 1980, and it sent theoretical physicists into a productive frenzy. CP violation was exactly one of the ingredients Sakharov had identified as necessary for baryogenesis. If nature treated matter and antimatter differently, even by a tiny amount, then perhaps that difference could explain why the universe ended up with more matter than antimatter. The crack in the mirror was not just a curiosity, it was a clue, possibly the most important clue in all of cosmology. Here is a quirky detail that rarely makes it into textbooks. When Cronin and Fitch first saw their result, they did not believe it. They spent months looking for errors, checking for contamination in their particle beam, recalibrating their detectors, and generally trying to make the anomaly go away. Fitch later recalled that they were almost disappointed when the result held up, because they knew it would cause enormous theoretical headaches. Discovering that a fundamental symmetry of nature is broken is not the kind of news that makes you popular at physics parties. It is the kind of news that makes everyone else's calculations wrong. But the headache was just beginning. CP violation in kaons was real but tiny, far too small to account for the matter-antimatter imbalance in the universe. Physicists needed more. They needed to know if CP violation appeared in other systems, if it was larger somewhere else, and whether there were deeper symmetry violations hiding beneath the surface. That search would take decades, lead to the construction of enormous particle factories in Japan and California, and eventually funnel back to a quiet experiment in Geneva, where a few hundred atoms of antihydrogen were about to change everything. You can feel the thread pulling now, connecting Dirac's equation to Anderson's cloud chamber, to Cronin's kaons, each discovery layered on the last like sediment in a riverbed. The river is flowing towards CERN, and you are drifting along with it. The river carries you now to the place where the story truly narrows and sharpens, where all those decades of theory and discovery converge into a single experimental hall buried beneath the Jura Mountains. You're inside CERN's antiproton decelerator facility, and the first thing that strikes you is how surprisingly modest it looks. After all that talk of fundamental symmetries and the origin of the universe, you might expect something cinematic, a cavernous space filled with pulsing lights and dramatic steam vents. Instead, you find a building that looks a bit like an unusually well-funded warehouse. There are concrete floors, exposed cable trays running along the ceiling, and a faint hum that you feel more in your teeth than in your ears. Scattered across the floor are clusters of equipment surrounded by scaffolding, each cluster belonging to a different experiment, and tucked among them, neither the largest nor the flashiest, is the Alpha apparatus. Alpha stands for Antihydrogen Laser Physics Apparatus, which is one of those acronyms that clearly had the cool name chosen first, and the words reverse engineered to fit afterward. Its purpose is deceptively simple to state, and monumentally difficult to execute. Alpha exists to create atoms of antihydrogen, trap them, and study their properties with enough precision to compare them to ordinary hydrogen. If antihydrogen behaves exactly like hydrogen in every measurable way, then CPT symmetry holds and physicists go home, mildly disappointed but intellectually secure. If antihydrogen deviates from hydrogen, even by the smallest measurable amount, then something is deeply wrong with our understanding of the universe, or deeply right, depending on your perspective. The heart of the alpha experiment is its trap, and the trap is a masterpiece of engineering that deserves a moment of appreciation as you settle deeper into your pillow. Imagine a cylindrical vacuum chamber about the size of a large thermos flask. Inside that chamber, a combination of electric and magnetic fields creates a three-dimensional cage with no physical walls. The magnetic field is generated by a series of superconducting coils arranged in a configuration called an octopole, which produces a field that is strongest at the edges and weakest in the center. Since antihydrogen atoms are neutral overall but still have a tiny magnetic moment, they behave like microscopic compass needles. Atoms in the right quantum state are attracted toward the region of the weakest field, which means they naturally drift toward the center of the trap and stay there. Atoms in the wrong quantum state are repelled and lost. The whole thing works only if the antihydrogen is extraordinarily cold, moving at speeds corresponding to a temperature of about 0.5 degrees above absolute zero. At those temperatures, the atoms drift so slowly that the gentle magnetic slopes of the trap are enough to contain them. Getting antihydrogen cold enough and calm enough to sit in that trap is where the real magic happens, and by magic you should understand that you mean years of painstaking effort by hundreds of people. The process begins far upstream in CERN's accelerator complex, where protons are slammed into a metal target to produce antiprotons. Those antiprotons come out screaming with energy, far too fast and hot to be useful. They are fed into the antiproton decelerator, a ring-shaped machine whose sole job is to slow them down. Think of it as the anti-accelerator, a machine that exists not to speed particles up but to cool them off. The antiprotons circle around and around, losing energy at each pass until they are slow enough to be extracted and sent to the experiments. But even after the antiproton decelerator does its work, the antiprotons are still too energetic for alpha's delicate trap. So in 2016, CERN commissioned an additional ring called ALINA, the extra-low energy antiproton ring, which takes the already slowed antiprotons and decelerates them further by a factor of 50. ALINA is a small, elegant machine, only about 30 meters in circumference, and it was a game-changer for antimatter experiments. Before ALINA, experiments captured perhaps 1 in 10,000 antiprotons delivered to them. After ALINA, that efficiency jumped by a factor of 10 or more. It was like upgrading from a leaky bucket to a proper net. Here is a historical fact that puts the whole enterprise in perspective. The first artificial antiprotons were produced at Berkeley in 1955, but it took until 1995 for anyone to combine antiprotons and positrons into actual atoms of antihydrogen. That achievement happened at CERN's low-energy antiproton ring, a predecessor to the current facility, and the resulting antihydrogen atoms were moving at nearly the speed of a light, far too fast to study. They smashed into the walls of the detector within microseconds of being born. Producing antihydrogen was one thing. Producing antihydrogen that sat still long enough for you to actually learn something from it was quite another, and that gap took an additional 15 years to close. Scholars still argue about exactly how much credit should go to the alpha collaboration versus the competing ATRAP experiment, which was also working on antihydrogen trapping during the same period. Scientific priority disputes are as old as science itself, and the race to trap antihydrogen was no exception. Both teams contributed essential techniques, and the history of who did what first is tangled enough that a definitive account would require its own documentary. What is beyond dispute is that in 2010, Alpha announced that it had trapped antihydrogen atoms for the first time, holding them for about 1/10 of a second. By 2011, they extended that to over 15 minutes. By 2016, they were performing spectroscopy on the trapped atoms, shining laser light on antihydrogen and measuring how it responded. A quirky detail that engineers on the experiment like to mention is that the entire trapping region, where these precious antiatoms float in magnetic suspension, is one of the coldest places in the known universe. The vacuum inside the trap is better than the vacuum of interstellar space, and the temperature is lower than the cosmic microwave background radiation that permeates the cosmos. For a brief moment, in a cylinder the size of a water bottle, CERN creates conditions that are more extreme than anything found naturally in the observable universe, all to hold a handful of atoms that would fit comfortably on the head of a pin if they would not immediately annihilate the pin, the table, and a measurable fraction of the surrounding laboratory. That is the stage. That is the instrument. And you're about to watch what happens when the musicians finally start to play. You're still inside that warehouse-like hall, but now the experiment is running, and the process of making antihydrogen unfolds with a patience that borders on the meditative. If you were watching in real time, you would mostly see people staring at computer screens, occasionally murmuring to each other, sipping coffee that has gone cold hours ago. The drama is all happening inside the apparatus, at scales too small to see and temperatures too cold to feel, and it begins with the antiprotons. The antiprotons arrive from Alina in bunches, little pulses of antimatter delivered every couple of minutes like packages from a very dangerous postal service. Each bunch contains a few million antiprotons, which sounds like a lot until you remember that a single grain of sand contains more atoms than there are antiprotons produced at CERN in an entire year. The antiprotons are injected into a device called a penning trap, which uses a combination of electric fields and a strong magnetic field to confine charged particles. Inside the penning trap, the antiprotons are mixed with a cloud of electrons, and here something wonderfully counterintuitive happens. The electrons are much lighter than the antiprotons, which means they radiate energy more efficiently when they move. As the antiprotons bounce around and collide with the electrons, they transfer energy to the electron cloud, which radiates that energy away as photons. The antiprotons cool down. This technique is called sympathetic cooling, and it is exactly as gentle as it sounds. The electrons act as a kind of thermal sponge, absorbing the antiproton's excess energy and quietly disposing of it. After a few minutes of this, the antiprotons are cold enough to be useful, drifting lazily in the trap at temperatures just a few dozen degrees above absolute zero. Meanwhile, on the other side of the apparatus, positrons are being prepared. The positrons come from a small radioactive source, typically sodium-22, which naturally emits positrons through beta plus decay. Remember that process from earlier, the one happening right now inside your own body courtesy of the potassium in your bones. Same physics, different source. The emitted positrons are collected, slowed down, and accumulated in their own trap, building up a cloud of a few million positrons swirling in a magnetic field like a tiny glowing fog. It takes patience. Each accumulation cycle takes several minutes, and the positrons have to be carefully cooled and compressed to make them dense enough for what comes next. The marriage of antiproton and positron happens in a region of the apparatus called the mixing trap. The cold antiprotons are gently nudged from their holding trap into the mixing region, where the positron cloud is waiting. This is not a violent collision. It is more like releasing fish into a pond. The antiprotons drift into the positron cloud, and occasionally, through a process that physicists describe with a characteristically unromantic term three-body recombination, an antiproton captures a positron and forms an atom of antihydrogen. The third body in the process is another positron which carries away the excess energy, allowing the newly formed antiatom to settle into a bound state. Here is where things get tricky, and here is where you appreciate the almost absurd difficulty of the whole enterprise. The mixing trap produces antihydrogen atoms. Yes, but it produces them in random quantum states, moving in random directions at random speeds. Most of them are too hot or in the wrong magnetic state to be caught by the octopole trap. They slam into the walls of the apparatus and annihilate, producing a small flash of pions and gamma rays that the detectors dutifully record. Out of the millions of antiprotons and positrons that go into each mixing cycle, only a handful of antihydrogen atoms, sometimes as few as 1 or 2, end up cold enough and in the right state to be trapped. On a really good day, alpha might trap 20 atoms in a single cycle. On a bad day, 0. Scholars still argue about whether better mixing techniques could dramatically improve this yield, or whether the physics of three-body recombination imposes a fundamental ceiling. Some groups have proposed using laser-cooled positrons or entirely different formation mechanisms, like charge exchange with positronium, to produce colder antihydrogen more efficiently. These ideas are being explored, but for now alpha works with what it has, and what it has is a painfully small number of antiatoms accumulated over many repeated cycles. Once the antihydrogen atoms are trapped, the real experiment begins. The positron clouds and antiproton clouds are cleared away, the electric fields are adjusted, and the trapped antiatoms are left floating in the magnetic bottle, alone and undisturbed. They can survive there for remarkably long periods. Alpha has held antihydrogen for over 16 hours, which is extraordinary when you consider that the atoms are surrounded by a vacuum chamber made entirely of matter that would annihilate them on contact. They survive because the magnetic trap keeps them hovering in the centre, never touching the walls, suspended in a void more empty than the space between stars. A delightful little quirk of this process involves the annihilation detector that surrounds the trap. When an antihydrogen atom does eventually escape the trap and hit the wall, it annihilates and produces a characteristic burst of particles. The detector picks up this burst and records it, giving the scientists a precise count of how many atoms were trapped. In a sense, the experiment counts its successes by counting its failures. Every atom that annihilates is an atom that was once trapped and then lost. The ones that remain are invisible and silent, floating in their magnetic cradle, waiting to be interrogated by a beam of precisely tuned laser light. And that laser light is where the next part of the story lives. Because holding antimatter is impressive, but it is just the beginning. The real question, the one that has been building since Dirac first noticed something strange in his equation, is whether that antimatter talks back in the same language as matter. You're about to find out how scientists learn to listen. The laser arrives like a whisper. Not a dramatic movie-style beam cutting through smoke, but a thread of ultraviolet light so precisely tuned that its frequency is known to 13 decimal places. You're watching the Alpha team perform spectroscopy on antihydrogen, and to appreciate what they're doing, you first need to understand why ordinary hydrogen is so important to physics, and why its spectrum is essentially the Rosetta Stone of the atomic world. Hydrogen is the simplest atom in existence. One proton, one electron, bound together by the electromagnetic force. That simplicity makes it the most precisely measured system in all of science. Over the past century and a half, physicists have measured the frequencies at which hydrogen absorbs and emits light to extraordinary accuracy. The most famous of these is the so-called 1s to 2s transition, which is the frequency of light needed to kick hydrogen's electron from its lowest energy state to a specific excited state. This transition has been measured in ordinary hydrogen to a precision of about 15 significant digits. 15. That is like measuring the distance from Earth to the Moon and being accurate to within the width of a single atom. It is the most precisely measured quantity in all of atomic physics, and it is the standard against which antihydrogen will be judged. The reason this particular transition matters so much is that it is extraordinarily narrow. In spectroscopy, narrow means precise. A narrow spectral line is like a sharp pencil mark on a ruler, easy to locate and hard to mistake. Broad lines are blurry, uncertain, difficult to pin down. The 1s to 2s transition in hydrogen is naturally narrow because the excited state is metastable, meaning the atom can sit in it for a relatively long time before dropping back down and emitting a photon. This long lifetime translates, through the Heisenberg uncertainty principle, into a very well-defined energy, which translates into a very well-defined frequency. It is the ideal target for a precision comparison between matter and antimatter. Alpha performs this measurement by shining a carefully tuned laser into the trapping region where the antihydrogen atoms float. The laser frequency is set very close to the expected 1s to 2s transition. If an antihydrogen atom absorbs the light, its positron jumps to the excited state. In that excited state, the atom's magnetic properties change, and it may no longer be confined by the trap. It drifts to the wall, annihilates, and the detector records the event. By scanning the laser frequency slowly across the expected resonance and counting how many atoms are lost at each frequency, the scientists build up a spectral line. The peak of that line tells them the transition frequency of antihydrogen. Now imagine doing this with 20 atoms, not 20,000, not 20 million, 20. Each measurement cycle takes hours. You accumulate antihydrogen, trap what you can, shine the laser, count the annihilations, clear the trap, and start over. The statistical power builds agonizingly slowly, one atom at a time. The alpha physicists have compared their work to trying to study the behavior of cats by observing one cat per week, each for about 10 seconds, and hoping to draw universal conclusions about feline nature. It is a joke, but it carries the weight of genuine frustration. Antimatter spectroscopy is the slowest, most painstaking form of measurement in modern physics. Despite these limitations, the results have been remarkable. Alpha first measured the 1s to 2s transition in antihydrogen in 2016 and found it consistent with hydrogen to a precision of about 2 parts in 10 billion. That was already a milestone, the first optical measurement of an antimatter atom. They improved steadily over subsequent years, tightening the error bars, refining their laser system, accumulating more data. Each new result was published to considerable fanfare and polite nods from the theoretical community, because each new result confirmed that antihydrogen looked exactly like hydrogen. CPT symmetry appeared to be holding. The mirror was intact. But spectroscopy is not just about one transition. Hydrogen has a rich spectrum with many lines, each corresponding to a different quantum jump. Alpha has also measured the hyperfine splitting of antihydrogen, which is the tiny energy difference caused by the interaction between the magnetic moments of the antiproton and the positron. This splitting is responsible for the famous 21 centimeter line in ordinary hydrogen, the radio frequency signal that astronomers use to map the distribution of hydrogen gas across the galaxy. Measuring the same splitting in antihydrogen is like checking the mirror from a different angle, testing a different aspect of the symmetry. Here is a historical fact that connects beautifully to this moment. The 21 centimeter hydrogen line was first predicted by the Dutch astronomer Hendrik van der Hulst in 1944 during the German occupation of the Netherlands. He was a graduate student at the time, and his advisor Jan Oort had asked him to look for spectral lines that might be useful for radio astronomy. Van der Hulst calculated that the hyperfine transition in hydrogen would produce radiation at a wavelength of about 21 centimeters, and when radio astronomers detected it in 1951, it opened an entirely new window on the universe. That same transition, 80 years later, is being measured in antimatter atoms at CERN. The thread runs unbroken from a graduate student in occupied Holland to a magnetic trap in Switzerland, connected by the simplest atom in existence and its ghostly twin. A quirky detail that spectroscopists enjoy sharing is that the laser used for the 1s to 2s measurement does not actually operate at the transition frequency. The transition requires ultraviolet light at a wavelength of about 243 nanometers, which is difficult to produce directly. Instead, alpha uses a technique called two-photon spectroscopy, where the atom absorbs 2 photons simultaneously, each at twice the wavelength. The laser operates in the visible range and the atom does the math itself, combining the 2 photons internally to make the quantum jump. It is an elegant trick, and it has the added benefit of eliminating first-order Doppler shifts, which would otherwise blur the measurement. Scholars still argue about whether future experiments should push for single-photon techniques at shorter wavelengths or continue refining the 2-photon approach, and the debate is far from settled. What is settled, what every member of the Alpha team knew in their bones as they collected data year after year, is that each measurement was a roll of the dice against the deepest symmetry in physics, and eventually the dice came up strange. The data arrived not with a bang but with a frown. You know that expression people make when they are reading something and the numbers do not quite add up? That slight tightening around the eyes, the unconscious tilt of the head. That is how it started, quietly, uncertainly. Someone on the Alpha team noticed that the latest batch of spectral measurements was not falling where it should. To set the scene properly, you need to understand what CERN had been doing in the years leading up to this moment. By the early 2020s, Alpha had accumulated an impressive body of measurements on antihydrogen, the 1s to 2s transition, the hyperfine splitting, the charge neutrality of the anti-atom, the behaviour of antihydrogen in a gravitational field. Each measurement had been consistent with hydrogen, each one a quiet confirmation that CPT symmetry was holding firm. The error bars were shrinking with every run, the precision improving as the team refined their techniques, upgraded their laser systems, and learned to trap more atoms per cycle. Everything was on track, everything was normal, and then it was not. The specific measurement that raised the alarm involved a more detailed analysis of the 1s to 2s spectral line shape. Previous measurements had focused primarily on the center frequency of the line, asking whether the peak of the antihydrogen resonance matched the peak of the hydrogen resonance, and it did, beautifully. But the new analysis went deeper. It looked at the wings of the spectral line, the regions on either side of the peak where the signal falls off towards zero. In ordinary hydrogen, the shape of these wings is predicted with exquisite precision by quantum electrodynamics, the theory that describes how light interacts with charged particles. The wings should be symmetric, falling off smoothly on both sides of the peak according to a well-known mathematical profile. In antihydrogen, the wings were not symmetric, not dramatically, not in a way that would make you drop your coffee, but persistently, across multiple datasets collected over several months, the spectral line of antihydrogen showed a subtle asymmetry that was not present in hydrogen. The low-frequency wing fell off slightly faster than the high-frequency wing, or perhaps the high-frequency wing extended slightly further than expected. The exact characterization depended on how the data was fitted, and the team spent weeks exploring different fitting models, different systematic corrections, different ways of slicing the data. The asymmetry remained. You can imagine the atmosphere in the collaboration meetings. Particle physics has a long and painful history of anomalies that turned out to be systematic errors. A cable plugged in wrong, a simulation with an incorrect assumption, a background process that was not properly accounted for. The most famous recent example was the faster-than-light neutrino result from the OPERA experiment in 2011, which electrified the world for months before being traced to a loose fibre optic cable and a miscalibrated clock. Nobody on the Alpha team wanted to be the next cautionary tale, so they checked everything. They checked the laser frequency calibration against an optical frequency comb, a device that provides a ruler for light frequencies with extraordinary precision. It was fine. They checked the magnetic field homogeneity inside the trap, because variations in the field could distort the spectral line shape. The field was within specifications. They checked for stray electric fields, which could cause stark shifts in the antiatom's energy levels. None were found above the expected threshold. They checked their Monte Carlo simulations, the computer models that predict how trapped antihydrogen atoms interact with the laser beam given their known temperature and spatial distribution. The simulations could not reproduce the observed asymmetry without introducing new physics. Scholars still argue, and will continue to argue for years, about whether all possible systematic effects have been fully excluded. This is the nature of precision measurement at the frontier. You are looking for a signal that is tiny compared to the dominant features of your data, and the list of things that could mimic such a signal is long. Every detector has quirks. Every magnetic field has imperfections. Every laser has a line width, a slight fuzziness in its frequency that must be accounted for. The Alpha team, to their credit, published their results with a thorough catalogue of systematic uncertainties, each one estimated and bounded. And even after all those uncertainties were folded in, the asymmetry persisted at a level that crossed the threshold of statistical significance. The number that matters here is the sigma level, and you will hear this term a lot in the coming months if the result holds up. In particle physics, sigma is a measure of how unlikely it is that the observed result is a statistical fluke. 1 sigma means there is roughly a 32% chance the result is random noise. Not interesting. 2 sigma means about a 5% chance. Eyebrow-raising but not convincing. 3 sigma, roughly a 0.3% chance, is considered evidence of something real. 5 sigma, a 1 in 3.5 million chance, is the gold standard for a discovery. The alpha result, as of the latest publication, sits at approximately 3.5 sigma. That is squarely in the territory physicists call interesting. It is above the threshold for evidence but below the threshold for discovery. It is, to use a metaphor that feels appropriate for this hour, the sound of a door creaking open in a house you were told was empty. Here is a fringe tidbit that adds texture to the moment. Some theorists had predicted exactly this kind of asymmetry years before the measurement was made. A small group working on extensions of the standard model that incorporate violations of Lorentz symmetry, the symmetry underlying Einstein's special relativity, had published papers suggesting that certain exotic interactions could produce detectable distortions in antimatter spectral lines. Those papers were largely ignored at the time because the predicted effects were tiny, and the experimental precision needed to see them was beyond what anyone had achieved. Now those papers are being pulled off shelves and read with fresh eyes, and their authors are experiencing the rare and intoxicating sensation of possibly having been right all along. The door is creaking, the house is not empty, and you are lying in the dark listening to the sound, wondering what is on the other side. You might be wondering, quite reasonably from the comfort of your pillow, what the word impossible actually means when a physicist says it. Because physicists use that word differently than the rest of the world. When your friend says it is impossible to eat just one potato chip, they mean it is difficult. When a physicist says a result is impossible, they mean it contradicts a specific, mathematically rigorous prediction made by a well-tested theory. The theory said this number should be 0, and the number is not 0. That is the kind of impossible we're dealing with tonight, and the distinction matters because it determines how seriously the scientific community takes the claim. The currency of believability in particle physics is the sigma level, and you already know that alpha's anomaly sits at roughly 3.5 sigma. But to really feel what that number means, you need to understand the culture surrounding it, because particle physics has developed an almost ritualistic relationship with statistical significance. The 5 sigma threshold for discovery was not handed down on a stone tablet. It emerged gradually through decades of hard experience, a community-wide agreement born from the painful memory of too many 3 sigma results that evaporated when more data arrived. 3 sigma sounds impressive until you remember that particle physics experiments typically look at many different measurements, many different distributions, many different ways of cutting the data. When you look at enough things, statistical flukes become almost inevitable. This is called the look elsewhere effect, and it is the bane of every experimentalist's existence. Imagine rolling 100 dice simultaneously. The odds of any specific die landing on 6 are 1 in 6. But the odds of at least one die landing on 6 are overwhelmingly high. If you then point to that one die and announce that something extraordinary has happened, you're fooling yourself. The look elsewhere effect is the statistical version of that fallacy, and physicists guard against it by demanding an absurdly high threshold before they claim a discovery. 5 sigma, 1 chance in 3.5 million, is high enough that even after accounting for the many places you looked, the result is still almost certainly real. At 3.5 sigma, alpha's result is not there yet. It is in the valley of maybe. This is the zone where physicists become simultaneously their most excited and most cautious, where every conversation at every conference includes the phrase, "if this holds up," uttered with a mixture of hope and dread. The history of this valley is littered with the wreckage of results that did not hold up. The pentaquark signals of the early 2000s, the diphoton excess at 750 GeV in 2015, the muon G-2 anomaly that fluctuated tantalizingly for years. Some of these eventually crossed the threshold, most did not. The Valley of Maybe is a well-populated graveyard. But here's what makes the alpha result different from many of those historical examples, and why the quiet panic in the theoretical community is more intense than usual. Most particle physics anomalies arise in collider experiments, where protons are smashed together at enormous energies and the debris is analysed for unexpected patterns. Those experiments are powerful but messy. The collisions produce hundreds of particles, and extracting a signal from that chaos requires sophisticated analysis techniques that introduce many opportunities for subtle errors. Alpha, by contrast, is a precision experiment. It does not smash anything. It holds a few atoms in a magnetic bottle and shines a laser on them. The measurement is conceptually simple, even if technically demanding. There are fewer places for systematic errors to hide, fewer knobs to turn, fewer assumptions to second guess. When a precision experiment sees something unexpected, the physics community pays closer attention because the result is harder to explain away. Scholars still argue about exactly where the burden of proof should lie in cases like this. Some physicists advocate for a Bayesian approach, where the prior probability of CPT violation is factored into the analysis. Since CPT symmetry has been confirmed in every previous test, the prior probability of a violation is very low, which means you need even stronger evidence to overturn it. Others counter that the prior should not be set too low, because our previous tests of CPT symmetry were nowhere near as precise as alpha's current measurements. Testing a symmetry to 1 part in a million and finding it intact does not tell you much about what happens at 1 part in a trillion. The debate is technical and ongoing, and it reflects a deeper philosophical disagreement about how science should weigh extraordinary claims against extraordinary evidence. A historical fact worth weaving in here is that the 5 sigma standard itself was partly a response to a specific embarrassment. In 1984, a team at CERN announced the discovery of a particle called the zeta, based on a signal that appeared to be statistically significant. The particle did not exist. The signal was a fluctuation, and its announcement and subsequent retraction damaged the credibility of the researchers involved. The experience left a scar on the institution, and the informal consensus that followed, demanding 5 sigma before anyone pops champagne, can be traced in part to that episode. CERN learned the hard way that the universe is perfectly capable of showing you what you want to see if you squint hard enough. And here is a quirky little detail about the psychology of sigma levels that experimentalists rarely discuss publicly but freely admit over drinks. When a result is at 2 sigma, you do not talk about it. When it is at 3 sigma, you start writing the paper but you hedge every sentence. When it hits 3.5, you cannot sleep, not because you are certain the result is real, but because you are standing on a knife edge. 1 more year of data could push it to 5 sigma and a Nobel Prize, or it could watch it slide back to 2 sigma and a footnote. 3.5 sigma is the most stressful number in physics. It is the scientific equivalent of a text message that says, "We need to talk." You do not know if it is good news or bad news, you only know it is not nothing. The Alpha team is living on that knife edge right now, collecting more data, refining their systematics, preparing for the next round of measurements. The answer is coming, and whether it confirms the anomaly or dissolves it, the process of getting there is a masterclass in how science actually works at the boundary of knowledge. Not with sudden eureka moments, but with years of careful, grinding, unglamorous work punctuated by the occasional heart-stopping blip on a screen. You breathe. The knife balances. The data accumulates. The knife rests on something deeper than statistics. It rests on a symmetry so fundamental that most physicists consider it the bedrock beneath the bedrock, the last floor in a building that has already lost several stories. That symmetry is called CPT, and if alpha's anomaly is real, it means this floor has a crack in it. To feel the full weight of that, you need to understand what CPT symmetry actually is, why physicists trust it so deeply, and what would happen to the entire edifice of modern physics if it turned out to be imperfect. You already met CP and T individually a few sections back, when Cronin and Fitch were breaking things in Long Island. C swaps particles for antiparticles. P flips the spatial mirror. T reverses the direction of time. Each of these symmetries can be violated on its own. The weak force violates P. The weak force violates C. The combination CP is violated in Carn, and B meson decays. Nature has shown, repeatedly, that it is willing to break these individual symmetries and even their pairwise combinations. But the triple combination, CPT, is different. CPT symmetry says that if you simultaneously swap all particles for antiparticles, flip the mirror, and reverse time, the laws of physics remain absolutely unchanged. Not approximately unchanged. Not unchanged to within some tolerance. Absolutely, exactly, perfectly unchanged. This is not merely an empirical observation. It is a theorem, proved mathematically from a small set of assumptions that underlie all of modern quantum field theory. The CPT theorem was established in the 1950s through the work of several physicists, most notably Julian Schwinger, Gerhard Luders, and Wolfgang Pauli. The proof rests on 3 pillars. First, the theory must be consistent with special relativity, meaning it must respect Lorentz symmetry. Second, the theory must be local, meaning interactions happen at specific points in space-time, rather than at a distance. Third, the theory must have a well-behaved vacuum state, meaning the lowest energy state of the system is stable. These 3 assumptions are so deeply embedded in the standard model that questioning any one of them feels like questioning the ground beneath your feet. And that is exactly why a CPT violation would be so catastrophic. If CPT is broken, then at least one of those three pillars must be wrong. Either Lorentz symmetry is not exact, or locality is not exact, or the vacuum is not what we think it is. Each of these possibilities opens a trapdoor into profoundly unfamiliar territory. Let us take them one at a time as you settle deeper into the covers. If Lorentz symmetry is violated, it means that the speed of light is not truly the universal speed limit in all reference frames. It means that the fabric of space-time has a preferred direction, a grain like wood. Moving along the grain would be subtly different from moving against it. This idea sounds radical, but there is an entire theoretical framework called the Standard Model Extension, developed primarily by Alan Kostelecki and colleagues at Indiana University, that parameterizes all possible Lorentz violations in a systematic way. The framework contains hundreds of coefficients, each one representing a different way that Lorentz symmetry could be broken. Most of those coefficients have been experimentally constrained to extraordinary precision and found to be consistent with zero, but not all of them. Some remain poorly tested, particularly those that would show up in comparisons between matter and antimatter at low energies. Alpha's anomaly, if confirmed, could be the first definitive non-zero measurement of one of those coefficients. Kostelecki himself has published papers analysing what specific Lorentz-violating effects alpha's measurement could constrain, and those papers are now being read with renewed urgency. If locality is violated, the implications are even stranger. Non-local interactions would mean that events at one point in space-time could directly influence events at another point without any signal travelling between them. This sounds like it might conflict with causality, the principle that causes precede effects, and indeed it might. Non-local theories exist, but they are deeply controversial and difficult to reconcile with the rest of physics. Scholars still argue about whether any consistent non-local quantum field theory can be constructed that preserves the other successes of the standard model while allowing CPT violation. The consensus for now is that this route is possible in principle, but fraught with technical difficulties. If the vacuum is unstable or has unexpected structure, the consequences are perhaps the most philosophically unsettling of all. The vacuum in quantum field theory is not empty. It is a seething soup of virtual particles popping in and out of existence, a foamy substrate that underlies everything. If the vacuum has properties we have not accounted for, hidden fields, unexpected symmetry breaking, exotic condensates, then CPT violation could emerge as a low-energy remnant of those hidden structures. Some string theory models predict exactly this, suggesting that the vacuum of our universe is one of an astronomically large number of possible vacua, and that the specific vacuum we inhabit might not respect all the symmetries that a generic vacuum would. This idea is speculative and difficult to test, but it connects the alpha anomaly to some of the deepest questions in theoretical physics. Here is a historical fact that gives this discussion some grounding. The CPT theorem was considered so robust that when physicists first discovered CP violation in 1964, they immediately concluded that T-symmetry must also be violated in exactly the right way to preserve CPT. This was not verified experimentally until 1998, when the CPL-EAR experiment at CERN directly observed T violation in the neutral kaon system. The reasoning was that if CPT holds and CP is broken, then T must be broken by exactly the same amount to compensate. And it was. That beautiful logical chain, that elegant balancing act, is exactly what alpha's result threatens to unravel. A quirky tidbit to carry with you as you drift. Wolfgang Pauli, one of the architects of the CPT theorem, was famous for his withering criticism of sloppy physics. He once dismissed a colleague's paper by saying it was not even wrong, meaning it was so vague it could not be tested. One wonders what Pauli would say about a 3.5 sigma anomaly in antihydrogen spectroscopy. Probably something devastating, probably something accurate, and probably something that would only make everyone more determined to collect more data and find out whether the floor is truly cracked or merely creaking under the weight of expectation. The floor creaks. You listen. The night deepens. You're now standing, metaphorically at least, inside the standard model of particle physics, and it is worth taking a moment to appreciate just how magnificent and how maddening this construction is. Because if CPT symmetry is cracked, the standard model is what cracks with it, and before you watch something break, you should understand what it looked like when it was whole. The standard model is the single most successful scientific theory ever created by human beings. That is not hyperbole. It is a factual assessment based on the sheer number and precision of its confirmed predictions. It describes 3 of the 4 fundamental forces of nature: electromagnetism, the strong nuclear force, and the weak nuclear force. It catalogues every known elementary particle, from the familiar electron to the exotic top quark, organized into a framework of such mathematical elegance that physicists sometimes call it the periodic table of particle physics. It predicted the existence of the W and Z bosons before they were discovered. It predicted the top quark before it was discovered. It predicted the Higgs boson roughly half a century before it was finally found at CERN in 2012, a discovery that completed the model's particle catalogue and earned Peter Higgs and François Englert the Nobel Prize. The precision of the standard model's predictions is almost obscene. The magnetic moment of the electron, a property related to how strongly it interacts with magnetic fields, has been calculated using the standard model to more than 10 significant digits. The experimental measurement agrees with that calculation to the same precision: 10 digits. That is like predicting the distance from New York to Los Angeles and being accurate to within the thickness of a human hair. No other theory in any branch of science has ever achieved that level of agreement between prediction and observation. And yet, for all its triumphs, the standard model is riddled with holes. Not small, polite holes that can be patched with a bit of theoretical spackle, but gaping, embarrassing holes that physicists have been staring at for decades with a mixture of frustration and admiration. The model has roughly 26 free parameters, numbers like the masses of the quarks and the strengths of the forces that the theory does not predict. They have to be measured experimentally and plugged in by hand. Why the electron has the mass it does, why the strong force is the strength it is, the standard model has no idea. It describes these values with beautiful precision, but explains none of them. It is like having a map that shows every road in a city but cannot tell you why the city is there. Then there is gravity. The standard model does not include gravity at all. The force that keeps your body pressed against the mattress right now, the force that governs the motion of planets and the collapse of stars and the expansion of the universe, is simply absent from the most successful particle physics theory ever written. Einstein's general relativity handles gravity beautifully at large scales, but nobody has managed to merge it with the quantum framework of the standard model in a consistent way. This failure, the inability to unify gravity with the other 3 forces, is arguably the single biggest unsolved problem in fundamental physics. Scholars still argue about whether the solution requires radically new mathematics, entirely new physical principles, or simply more patience. And then there is the embarrassment of cosmic proportions that connects directly to tonight's story. The standard model cannot explain why you exist. Remember the matter-antimatter asymmetry, the 1 in a billion surplus that survived the Big Bang. The standard model contains CP violation, which is one of Sakharov's necessary ingredients, but the amount of CP violation in the standard model is vastly insufficient to produce the observed surplus. The numbers are off by 10 orders of magnitude. the standard model can generate a slight preference for matter over antimatter, but it is like trying to empty a swimming pool with an eyedropper. Technically, you are making progress. Practically, you're going to be there until the heat death of the universe. There is also the dark sector. Astronomical observations have established beyond reasonable doubt that the ordinary matter, described by the standard model, the atoms, the molecules, the stars, the galaxies, everything you can see and touch, accounts for roughly 5% of the total energy content of the universe. About 27% is dark matter, a mysterious substance that exerts gravitational influence but does not interact with light. The remaining 68% is dark energy, an even more mysterious phenomenon driving the accelerating expansion of the universe. The standard model describes none of this. It is a theory of the 5%. It is exquisitely detailed about the visible minority and completely silent about the invisible majority. Here is a quirky little detail that captures the frustration beautifully. The Higgs boson, whose discovery in 2012 was celebrated as the capstone of the standard model, actually made things worse in a certain sense. The Higgs mass came in at roughly 125 gigaelectron-volts, a value that sits in an awkward no-man's land. It is too light to be natural within the standard model without extreme fine-tuning of the theory's parameters, a problem known as the hierarchy problem. Many physicists expected that the Large Hadron Collider would discover new particles alongside the Higgs, particles predicted by extensions of the standard model like supersymmetry that would resolve the fine-tuning issue. No such particles have appeared. The desert, as physicists gloomily call it, stretches from the Higgs mass upward with no new oases in sight. A historical fact that adds weight to the moment. When the standard model was being assembled in the 1960s and 70s, its architects, people like Sheldon Glashow, Abdus Salam, and Steven Weinberg, did not expect it to last this long. They thought it was a low-energy approximation, a stepping stone to a deeper theory that would reveal itself at higher energies. Instead, the standard model has stubbornly refused to break, passing every experimental test thrown at it while simultaneously failing to answer the biggest questions in physics. It is the most successful failure in the history of science, or perhaps the most frustrating success, and that is why the alpha anomaly has sent a tremor through the community. The standard model needs to break somewhere. Something has to give. The universe is practically begging for new physics, and a CPT violation in antihydrogen spectroscopy would be exactly the kind of crack that could let the light in. You lie there in the dark, and somewhere beneath Switzerland the crack may already be forming. The darkness around you is appropriate because the universe itself is mostly dark, and the next piece of this puzzle lives in that darkness. You have just seen the standard model in all its flawed glory, a theory that describes the visible 5% of reality with extraordinary precision while having absolutely nothing to say about the other 95%. That missing 95%, the dark matter and dark energy that dominate the cosmos, is the elephant in the room of modern physics. And some physicists are now wondering whether the strange behaviour of antimatter at CERN might finally offer a flashlight to shine into that enormous dark. Dark matter announced itself through gravity. In the 1930s, the Swiss astronomer Fritz Zwicky was studying the Coma cluster, a massive collection of galaxies about 300 million light-years from Earth. He measured the velocities of the galaxies within the cluster and found that they were moving far too quickly to be held together by the gravitational pull of the visible matter alone. The galaxies should have flown apart like sparks from a firework. Something invisible was providing extra gravitational glue, and Zwicky called it dunkle Materie, dark matter. His colleagues mostly ignored him, partly because the evidence was thin and partly because Zwicky was, by all accounts, extraordinarily difficult to work with. He reportedly called his fellow astronomers spherical bastards, because they were, he explained, bastards no matter which direction you looked at them. It took another 4 decades for dark matter to become respectable. In the 1970s, the American astronomer Vera Rubin measured the rotation curves of spiral galaxies and found the same discrepancies Wiki had seen, but with much better data. Stars at the edges of galaxies were orbiting just as fast as stars near the centre, which was physically impossible unless a vast halo of invisible matter surrounded each galaxy. Rubin's work, combined with subsequent observations of gravitational lensing, the cosmic microwave background, and the large-scale structure of the universe, established dark matter as one of the most well-supported yet least understood phenomena in all of science. Scholars still argue about whether Rubin was unfairly denied the Nobel Prize before her death in 2016, and the consensus among many physicists and historians is that she absolutely deserved it. So what is dark matter? Nobody knows. That 3-word sentence contains more frustration per syllable than almost any other sentence in modern physics. Decades of experiments have searched for dark matter particles using detectors buried deep underground to shield them from cosmic rays, using satellites orbiting Earth, using the Large Hadron Collider itself. None have produced a definitive detection. The leading candidate for many years was a hypothetical particle called the WIMP, the weakly interacting massive particle, which would interact with ordinary matter only through gravity and the weak force. WIMPs were attractive because they naturally appeared in supersymmetric extensions of the standard model, and because their predicted abundance matched the observed dark matter density with suspicious precision, a coincidence physicists called the WIMP miracle. But as searchers grew more sensitive and found nothing, the miracle began to look less miraculous and more like a mirage. This is where antimatter enters the dark sector conversation, and where the alpha anomaly becomes relevant in a way that extends far beyond spectroscopy. Several theoretical frameworks have proposed that dark matter interacts differently with matter and antimatter. If CPT symmetry is exact, this would be impossible. Any force that couples to matter must couple to antimatter in precisely the same way, just with the appropriate signs flipped. But if CPT symmetry is broken, even slightly, then the door opens to asymmetric dark sector interactions. Dark matter could exert a subtle pull on antihydrogen that it does not exert on hydrogen, or vice versa. This pull would shift the energy levels of antihydrogen by a tiny amount, producing exactly the kind of spectral anomaly that alpha has observed. The idea is speculative, and you should hold it loosely, the way you hold a thought at 2 a.m. when your critical faculties are pleasantly dimmed. But it is not fringe. Serious theorists at serious institutions have published papers exploring this possibility, and the mathematics is internally consistent. One particular class of models involves a hypothetical field called a CPT-violating background field, which permeates all of space and interacts differently with particles and antiparticles. This field would be invisible to most experiments, but would leave a fingerprint in high-precision comparisons between matter and antimatter. Alpha's anomaly could be that fingerprint. Dark energy is even more mysterious than dark matter, and its connection to antimatter is more tenuous but no less intriguing. Dark energy is whatever is causing the expansion of the universe to accelerate, a discovery made in 1998 by 2 independent teams studying distant supernovae. The simplest explanation is a cosmological constant, a fixed energy density inherent to empty space itself. But the value of this constant, when calculated from quantum field theory, comes out roughly 120 orders of magnitude too large. This is the cosmological constant problem, and it is often described as the worst theoretical prediction in the history of physics. Some speculative models suggest that a better understanding of vacuum symmetries, including CPT, could help resolve this catastrophic disagreement. Here is a quirky tidbit that connects the cosmic and the microscopic in a way that feels appropriate for this hour. The energy released by annihilating a single kilogram of antimatter with a kilogram of matter is roughly equivalent to the energy released by the largest nuclear weapons ever detonated. About 43 megatons of TNT, the entire annual energy consumption of a small country, released from 2 lumps of stuff that would fit in your hands. And yet all the antimatter CERN has ever produced in its entire history of operation amounts to roughly 20 nanograms. If you annihilated all of it at once, you would get enough energy to boil a cup of tea. Maybe 2 cups if you were optimistic. The gap between antimatter's theoretical potential and its practical availability is one of the great cosmic jokes. A universe that hands you the most powerful energy source imaginable and then makes it almost impossible to collect. You smile at that thought, or maybe you do not. Maybe you're already halfway to sleep. Either way, the darkness around you has taken on a new quality. It is not just the absence of light. It is a reminder that the universe is mostly made of things you cannot see, things that do not appear in any textbook, things that the standard model cannot name, and somewhere in that darkness, antimatter might be whispering secrets about what hides there. The whisper gets louder now, and it takes a surprising direction. Downward. Because while Alpha was busy shining lasers on trapped antihydrogen and finding spectral anomalies, a sibling experiment just a few meters away was asking an entirely different question about antimatter. Not how it absorbs light, but how it falls. Does antimatter obey gravity the same way as matter? Does an anti-apple fall from an anti-tree at the same rate as Newton's original? The experiment is called Alpha G, and its results carry implications that intertwine with the spectral anomaly in ways that are still being untangled. The question might sound absurd at first. Gravity is gravity, right? Everything falls at the same rate. Galileo supposedly demonstrated this by dropping balls from the Leaning Tower of Pisa, though scholars still argue about whether that event actually happened, or is an embellishment added by his biographer decades later. What is not disputed is the principle. In the absence of air resistance, a feather and a hammer hit the ground at the same time. Apollo 15 astronaut David Scott demonstrated this on the Moon in 1971, dropping a falcon feather and a geology hammer in the lunar vacuum and watching them land together. The principle of equivalence, the idea that gravitational mass and inertial mass are identical, is one of the cornerstones of Einstein's general relativity. It has been tested with ordinary matter to extraordinary precision and found to hold in every case. But nobody had ever tested it with antimatter, not directly. The reason is practical. Antimatter annihilates on contact with matter, which makes it rather difficult to put on a scale or drop from a tower. Any antimatter experiment involving gravity needs to work with neutral antiatoms, since charged antiparticles would be overwhelmed by stray electromagnetic forces that are billions of times stronger than gravity. You need antihydrogen, and you need it cold and trapped and plentiful enough to perform a statistical measurement. Until Alpha came along, none of those conditions could be met. Alpha G is a vertical extension of the Alpha apparatus, designed specifically to release trapped antihydrogen atoms and watch which way they drift. The setup is ingenious in its simplicity. You take your magnetically trapped antihydrogen, slowly reduce the strength of the confining fields, and let the atoms escape. As they escape, they can drift either upward or downward. Detectors at the top and bottom of the trap record where the atoms annihilate. If more atoms hit the bottom, antimatter falls down just like matter. If more hit the top, antimatter falls up, and physics has a very serious problem. The result, published in 2023, was both reassuring and tantalizing. Antimatter falls down. antihydrogen responds to Earth's gravity in the same direction as ordinary hydrogen. The measurement confirmed, for the first time in history, that antimatter is gravitationally attracted to matter rather than repelled by it. This ruled out the most exotic possibility, anti-gravity, which would have been genuinely revolutionary, but was always considered unlikely by most theorists. General relativity does not naturally accommodate repulsive gravity between matter and antimatter, and most physicists expected the result alpha G delivered. But the precision of the measurement left room for subtlety. Alpha G confirmed that antimatter falls down, but the exact rate of that fall, the gravitational acceleration experienced by antihydrogen, was measured with an uncertainty of about 25%. That means the experiment established that antihydrogen's gravitational acceleration is somewhere in the ballpark of Earth's standard gravitational acceleration, but could not yet confirm that it is exactly the same. A small difference, say a few percent, would be consistent with the data and would represent a violation of the equivalence principle for antimatter. Such a violation would not mean anti-gravity, but it would mean that antimatter and matter do not experience gravity identically, which would be nearly as revolutionary. Here is where the spectral anomaly and the gravity measurement begin to talk to each other. Several theoretical models that predict CPT violation also predict violations of the equivalence principle. This is because both CPT symmetry and the equivalence principle are rooted in the same underlying structure of spacetime. If spacetime has a grain, a preferred direction, or a subtle anisotropy that distinguishes matter from antimatter, it could manifest both as a spectral shift in antihydrogen and as a slight difference in gravitational behaviour. The two measurements are probing different faces of the same, potentially cracked crystal. A quirky detail about the alpha G experiment that engineers love to share involves the challenge of aligning the apparatus vertically. When you're measuring the gravitational freefall of atoms that move at fractions of a meter per second, the orientation of your trap relative to true vertical matters enormously. The alpha G team used a combination of precision survey instruments and seismometers to align their trap to within milliradians of true vertical, accounting for the fact that the local gravitational field at CERN is not perfectly uniform. The nearby Jura Mountains exert a tiny but measurable gravitational pull that tilts the local vertical slightly toward the northwest. You're lying in bed thinking about antimatter, and somewhere in Switzerland, the mass of a mountain range is a systematic error in a gravity experiment. The universe is wonderfully interconnected at every scale. Scholars still argue about how much can be inferred from alpha G's first result. Some physicists caution that the 25% uncertainty is far too large to draw any conclusions about equivalence principle violations, and that alpha G needs at least another decade of upgrades and data collection before it can compete with the precision of equivalence principle tests using ordinary matter. Others counter that even a rough measurement of antimatter gravity is groundbreaking, and that the directional confirmation alone eliminates entire classes of alternative theories. The truth, as you might expect by now, lies somewhere in the middle, tangled up in error bars and theoretical assumptions. What is clear is that CERN now has two independent handles on the matter-antimatter question. One is spectroscopic, comparing the light emitted and absorbed by antihydrogen with the light emitted and absorbed by hydrogen. The other is gravitational, comparing how antihydrogen falls with how hydrogen falls. If both measurements eventually reveal discrepancies, and if those discrepancies are consistent with each other and with a specific theoretical framework, then the case for new physics becomes extraordinarily strong. Two independent anomalies pointing in the same direction would be much harder to dismiss than either one alone. The blanket pulls tighter, the mountain exerts its pull. And beneath your comfortable weight, gravity does exactly what it has always done, faithful and predictable. But for antimatter, The question of faithfulness remains deliciously open, the theorists not sleeping either. Somewhere in offices and apartments scattered across a dozen countries, people with chalkboards and laptops and an unhealthy relationship with caffeine are working through the night, trying to build a framework that can explain what Alpha has seen, because an experimental anomaly without a theoretical explanation is like a crime scene without a suspect. Interesting, certainly. Troubling, absolutely. But ultimately unsatisfying until someone can point at a mechanism and say, that is what did it. The scramble to explain the Alpha result has turned into an intellectual buffet, and you're about to sample the main courses. The first dish on the table is supersymmetry, known affectionately as SUSY, the theory that has been the darling of theoretical particle physics for nearly 50 years, and the disappointment of experimental particle physics for nearly as long. Supersymmetry proposes that every known particle has a heavier partner particle with a different spin. For every fermion, a boson. For every boson, a fermion. The electron has a selectron. The quark has a squark. The photon has a photino. The names sound whimsical, and they are, but the mathematics is serious and deeply elegant. Supersymmetry naturally solves the hierarchy problem. It explains why the Higgs mass is not driven to enormous values by quantum corrections, and provides a natural candidate for dark matter in the form of the lightest supersymmetric particle. The problem, the elephant wearing a tutu in the middle of the theoretical ballroom, is that nobody has ever found a supersymmetric particle. The Large Hadron Collider has searched extensively, probing energy scales where the most popular versions of SUSY predicted new particles should appear, and has found nothing. This has forced theorists to push the predicted masses of supersymmetric particles higher and higher into energy ranges that the LHC cannot reach, which progressively undermines the theory's original motivation. A solution to the hierarchy problem that requires fine-tuning to explain why the solution itself is invisible is not a very satisfying solution, but some versions of supersymmetry, particularly those that include CP-violating phases in the supersymmetric sector, could produce subtle effects in antimatter spectroscopy. The idea is that virtual supersymmetric particles that flicker in and out of existence according to the quantum uncertainty principle, could shift the energy levels of antihydrogen by amounts that differ from the shifts they produce in hydrogen. The effect would be extraordinarily small, right at the edge of alpha's sensitivity. Whether it could produce the specific spectral asymmetry alpha observed is an active area of calculation, and the papers are appearing at a rate of roughly one per week. The second dish is extra dimensions. String theory, the most ambitious attempt to unify all forces including gravity, requires the existence of additional spatial dimensions beyond the three you experience. These dimensions are typically assumed to be curled up into tiny shapes, too small to detect directly, but their existence could have indirect consequences at low energies. In certain string-theoretic models, the geometry of the extra dimensions can break CPT symmetry spontaneously, much the way a perfectly symmetric pencil balanced on its tip will eventually fall in one direction and break its rotational symmetry. If the extra dimensions have a specific topology, a specific shape and structure, they could generate CPT-violating effects that show up precisely in the kinds of measurements alpha is performing. This is speculative terrain, and scholars still argue vigorously about whether string theory makes testable predictions at all, let alone predictions specific enough to match a particular spectral anomaly. The string theory landscape, the vast space of possible solutions that the theory permits, contains an estimated 10 to the power of 500 distinct vacua. Finding the one that matches our universe is less like searching for a needle in a haystack, and more like searching for a specific grain of sand on a beach the size of the observable universe. Critics call this the landscape problem and argue that a theory that can accommodate almost any result effectively predicts nothing. Supporters counter that the landscape is a feature, not a bug, and that the specific patterns of symmetry violation that string theory permits are distinct from those predicted by other frameworks. The third dish, and the one that has been generating the most excitement in the week since the alpha result, is Lorentz violation. You encountered this briefly when discussing the CPT theorem, but it deserves a closer look. Lorentz symmetry is the mathematical expression of Einstein's principle that the laws of physics look the same to all observers moving at constant velocity. It is built into the foundations of both special relativity and quantum field theory. But what if it is only approximately true? What if space-time itself has a subtle texture, a preferred frame, a background field that picks out a specific direction, or a specific rest frame as special? The standard model extension, the framework developed by Kostelecki and collaborators, parametrizes every possible way that Lorentz symmetry could be broken in the context of known physics. It is essentially a master catalogue of deviations, each one associated with a coefficient that experiment can constrain. Many of these coefficients affect matter and antimatter differently, which means precision comparisons between hydrogen and antihydrogen are among the most sensitive tests of Lorentz violation available. Alpha's anomaly, if interpreted within this framework, would correspond to a specific non-zero value for one or more of these coefficients. Several theorists have already published preliminary fits, and the results are intriguing. The anomaly is consistent with a particular type of Lorentz violation that would be extremely difficult to detect in any other experiment. A historical fact that adds texture here is that Lorentz symmetry was nearly abandoned before it was established. When Lorentz first proposed his transformations in the late 1890s, they were intended to explain the null result of the Michelson-Morley experiment, which had searched for the luminiferous ether and found nothing. Einstein's 1905 paper reinterpreted Lorentz's mathematics as a fundamental property of spacetime rather than a dynamical effect of motion through an ether. The irony is that some modern Lorentz violation models effectively reintroduce a kind of ether, not the mechanical fluid the Victorians imagined, but a quantum field that fills all of space and defines a preferred frame. The ghost of the ether, exercised by Einstein, may be creeping back in through the spectral lines of antihydrogen. A quirky fringe tidbit to carry with you. One class of Lorentz violation models predicts that the magnitude of the effect should vary with the orientation of the experiment relative to the fixed stars, changing subtly as the Earth rotates and orbits the Sun. Alpha's trap is fixed in the laboratory frame, which means it sweeps through different orientations as the planet turns. If the anomaly is truly due to Lorentz violation, its magnitude should show a tiny daily modulation. The Alpha team is already looking for this signature in their data, though the statistical power needed to detect a modulation on top of an already marginal signal is formidable. The buffet is rich, the theorists are feasting, and you are drifting gently through their arguments, sampling each one, not needing to choose, just letting the ideas settle around you like snow. The theories are elegant, the mathematics is beautiful, but none of it exists without the people who build the machines and run the experiments. And this is where the story of CERN's antimatter program becomes something more than physics. It becomes a story about human stubbornness, quiet sacrifice, and the particular kind of devotion that keeps a person working underground for years on a result they might never live to see. You do not hear much about these people in the headlines. When a major physics result is announced, the press coverage focuses on the discovery itself, maybe on the lead spokesperson who presents it at a conference, occasionally on the Nobel laureate who predicted it decades earlier. But behind every headline is a collaboration list, a document that can run to several hundred names, each one representing a person who contributed something essential. Alpha's collaboration includes physicists, engineers, technicians, graduate students, and postdoctoral researchers from institutions spanning North America, Europe, and Asia. The youngest are in their mid-20s, just starting their careers. The oldest have been working on antimatter for over 30 years. They're bound together by a shared obsession with a substance that annihilates everything it touches, which, if you think about it, is a reasonably good metaphor for the effect of academic physics on your social life. Consider the postdocs. These are researchers who have completed their doctoral degrees and are working on temporary contracts, typically 2 to 3 years, at institutions far from home. A postdoc on Alpha might spend 2 years living in a rented apartment near Geneva, commuting to the lab by bicycle, working 12-hour shifts during beam time when the antiproton decelerator is running, and then spending months analysing data in a windowless office. The pay is modest, the hours are brutal, the career prospects are uncertain, because academic physics has far more qualified candidates than permanent positions. For every postdoc who lands a faculty job, several others leave the field entirely, taking their expertise into finance or technology or teaching. The attrition rate is staggering, and it represents an enormous loss of trained talent that the physics community has never adequately addressed. Scholars still argue about whether the current academic system, with its reliance on temporary positions and hyper-competitive job markets, is sustainable or even ethical. Some advocate for more permanent staff scientist positions, modelled on the career structure at national laboratories like CERN itself. Others contend that the competition drives excellence and that softening the system would lower the quality of research. The debate is old, unresolved, and deeply personal for anyone who has lived through it. Then there are the engineers, the people who design and build the actual hardware. The Alpha Trap did not emerge fully formed from a theorist's notebook. It was designed, prototyped, tested, redesigned, rebuilt, and refined over years of iterative work. The superconducting magnets that generate the octopole field were custom built and required thousands of hours of winding, testing, and quality control. The ultra-high vacuum system that keeps the interior of the trap free of stray gas molecules required seals and pumps and bake-out procedures that push the limits of material science. The laser system that interrogates the trapped atoms required optics polished to fractions of a wavelength and frequency stabilization systems that reference atomic clocks. Each of these subsystems was someone's primary responsibility, someone's years-long project, someone's source of pride and frustration, and occasional late-night despair when a component failed and had to be replaced. A historical fact that illuminates the human dimension of big science is the story of the Bevatron, the accelerator at Berkeley that produced the first antiprotons in 1955. The Bevatron was designed by Ernest Lorentz's team and cost roughly $10 million, an enormous sum in the early 1950s. The machine employed dozens of engineers and technicians, many of whom spent their entire careers maintaining and operating it. When the antiproton was discovered, the Nobel Prize went to Emilio Segre and Owen Chamberlain, the lead physicists. The engineers who built the machine received neither credit nor recognition, beyond a mention in the acknowledgements section of the paper. This pattern has repeated itself throughout the history of particle physics, and it reflects a persistent bias in how society values different types of intellectual contribution. Here is a quirky detail about life on the Alpha experiment that captures the texture of daily work. During beam time, when the antiproton decelerator is delivering antiprotons, the experiment runs around the clock in shifts. The night shift, typically midnight to 8 in the morning, is notorious for being simultaneously the most productive and the most surreal period. The accelerator complex is quieter at night, which means fewer vibrations and better data quality. But the humans operating the experiment are running on coffee and willpower, and the logbook entries from late-night shifts sometimes contain observations that range from the scientifically precise to the existentially confused. One famous entry, which has been passed around the collaboration as a kind of inside joke, reportedly reads simply, "Trapped 3 atoms, lost 1, found a spider in the laser enclosure. Spider is fine." The mundane and the extraordinary coexist at CERN in a way that is difficult to convey to anyone who's not experienced it. The graduate students deserve a special mention because they are the ones who do the most grinding work with the least job security. A typical doctoral thesis on alpha might involve spending 3 to 4 years developing a single improvement to the trapping system, testing it, characterizing it, and then using it to collect a fraction of the data that eventually contributes to a published result. The student's name will appear on the collaboration's papers, buried among 100 others, and their thesis will describe their specific contribution in exhaustive detail that perhaps a dozen people will ever read. And yet, these students are the lifeblood of the experiment. Without their labour, their creativity, their willingness to work on problems that senior physicists consider too tedious or too risky, the experiment would grind to a halt. You lie in the dark and think about that for a moment. Somewhere under the Swiss countryside right now, someone is probably sitting in front of a monitor, watching a slow accumulation of positrons, sipping lukewarm coffee, thinking about whether the anomaly is real. They might be 26 years old. They might be far from home. They might be wondering if this is the discovery that changes everything, or the systematic error that teaches them humility. Either way, they are there, in the quiet hum of the laboratory, doing the work. And that work, unglamorous and unsung, is what makes the impossible merely difficult. From the quiet hum of the laboratory to the deafening roar of Hollywood, the journey antimatter has taken through popular culture is a story of magnificent misunderstanding. You have almost certainly encountered antimatter in fiction long before you ever heard about it in a physics context, and the version you encountered was, to put it gently, creative. To put it less gently, it was nonsense. Beautiful, entertaining, wildly profitable nonsense. But nonsense all the same, and comparing what popular culture thinks antimatter is with what it actually is provides one of those delightful contrasts that makes science communication so necessary and so often futile. The most famous fictional use of antimatter is almost certainly the warp drive in Star Trek. Since the original series premiered in 1966, the Starship Enterprise has been powered by the controlled annihilation of matter and antimatter, mediated by a fictional substance called dilithium crystal. The idea is simple and, on its surface, not entirely crazy. Matter-antimatter annihilation really is the most efficient energy conversion process known to physics, converting 100% of the input mass into energy, compared to nuclear fission at less than 1% and nuclear fusion at roughly 0.7%. If you could produce and store antimatter in bulk, it would indeed be an extraordinary fuel source. The problem, and this is where Star Trek waves its hands and changes the subject, is production. CERN's entire antimatter output over decades of operation amounts to roughly 20 nanograms. To fuel a spacecraft, you would need tons. Producing a single gram of antimatter using current technology would cost approximately $62 trillion and require roughly 25 million billion kilowatt-hours of energy. That is more energy than the entire world consumes in a year, devoted to making a quantity of antimatter that would fit on a fingertip. The energy balance is catastrophically negative. You put in vastly more energy making the antimatter than you could ever get back by annihilating it. It is like spending $1 million to manufacture a battery that holds a single dollar's worth of charge. Star Trek's warp drive is not just beyond current engineering. It requires a method of antimatter production that violates no laws of physics, but is so far from practical reality that it might as well be magic. Then there is Dan Brown's Angels and Demons, published in 2000 and adapted into a film starring Tom Hanks in 2009. The plot revolves around a quarter gram of antimatter stolen from CERN and fashioned into a bomb that threatens to destroy Vatican City. The antimatter is suspended in a portable magnetic trap powered by a battery, and the tension comes from the battery running down. When it dies, the antimatter contacts the container, annihilates, and boom! The physics of the annihilation is roughly correct. A quarter gram of antimatter annihilating with a quarter gram of matter would release energy equivalent to about 10 kilotons of TNT, comparable to the bomb dropped on Hiroshima. But the premise is absurd for reasons you already understand. CERN has never produced anything close to a quarter gram of antimatter. The total amount produced in the facility's entire history would not power a flashlight, let alone level a city. When the novel was published, CERN's press office gamely fielded hundreds of phone calls from concerned citizens who had read the book and wanted to know if the Vatican was in danger. The answer, delivered with the weary patience that CERN's communications team has perfected over decades, was no. A historical fact that connects fiction to reality in an amusing way involves the television show Star Trek itself. Gene Roddenberry, the show's creator, consulted with physicists when developing the series' technological concepts, and the choice of matter-antimatter annihilation as the Enterprise's power source was not random. It was based on real physics, filtered through the sensibility of a television producer who needed something that sounded scientific and looked dramatic on screen. The show's technical manual, published in 1975, contains surprisingly detailed diagrams of the warp drive system, complete with antimatter containment pods and magnetic constriction segments. These diagrams were drawn by fans and consultants who took the fictional technology far more seriously than Roddenberry probably intended, and they have inspired generations of physicists and engineers. Several researchers working at CERN today have admitted, with varying degrees of sheepishness, that Star Trek was their gateway to physics. Here is a quirky tidbit about antimatter in pop culture that rarely gets mentioned. The 1968 science fiction novel Antimatter by the Czech writer Vladimír Párl is not actually about antimatter at all. It is a satirical novel about a chemist navigating the absurdities of life in communist Czechoslovakia, and the title is a metaphor for the protagonist's sense of being the opposite of everything around him. The book has nothing to do with particle physics, but it occasionally appears in search results alongside genuine physics texts, confusing students and delighting librarians. The gap between fictional antimatter and real antimatter extends beyond energy and quantity into the realm of storage. In fiction, antimatter is typically stored in sleek containers with glowing blue interiors and ominous countdown timers. In reality, antimatter is stored in vacuum chambers surrounded by unglamorous superconducting magnets, cables and monitoring equipment that look like they belong in an industrial refrigeration plant. The alpha trap, where the atoms that may have cracked CPT symmetry float in magnetic suspension, would not look out of place in a brewery. There is no glow. There is no hum that you can hear from across the room. The drama is entirely internal, playing out at scales too small to see and energies too low to feel, recorded by detectors that produce nothing more cinematic than a histogram on a computer screen. Scholars still argue about whether science fiction helps or hinders public understanding of real science. Some contend that fictional depictions, however inaccurate, inspire curiosity and lead people toward genuine knowledge. Others worry that persistent fictional tropes create misconceptions that are difficult to correct, particularly around topics like antimatter, where the real science is less visually spectacular than the fiction. The truth probably depends on the individual. For every person who read Angels and Demons and then looked up how antimatter actually works, there is another who walked away believing CERN has a doomsday weapon in its basement. You smile in the dark, thinking about warp drives and Vatican explosions, and the reality that the most dangerous thing at CERN is probably the coffee. The actual revolution, the quiet one, is happening 20 atoms at a time in a magnetic bottle the size of a thermos. No countdown, no glow, just data, patience, and the nagging suspicion that the universe is stranger than any fiction ever imagined. The thermos-sized trap is not going to stay thermos-sized forever. The future of antimatter research at CERN is already being planned, and the machines that will succeed Alpha are designed to push the precision of antimatter measurements so far beyond current capabilities that the anomaly you've been hearing about tonight will either be confirmed beyond doubt or dissolved into statistical noise. Either outcome would be historic, but the path to getting there involves engineering challenges that make the current experiment look like a warm-up exercise. The most immediate upgrade is to Alpha itself. The collaboration has been developing what they call Alpha 3, a next-generation trapping system that incorporates several major improvements over the current apparatus. The new trap will have a larger trapping volume, allowing more antihydrogen atoms to be confined simultaneously. It will use improved superconducting magnets with better field homogeneity, reducing systematic effects that currently limit spectroscopic precision. And it will incorporate a new laser system capable of driving additional transitions in antihydrogen, opening up entirely new spectral lines for comparison with hydrogen. The goal is to improve the precision of the 1s to 2s measurement by at least an order of magnitude, pushing into the regime where the observed anomaly would either grow in significance or vanish entirely. If 3.5 sigma becomes 6 sigma with better data, the discovery is real. If it drops to 1 sigma, it was a fluctuation, and physicists will exhale and move on. But Alpha 3 is just the beginning. CERN has approved a broader program of antimatter experiments that extends well into the next decade. The base experiment, which focuses on precision measurements of the antiproton's magnetic moment, is pursuing its own comparisons between matter and antimatter with complementary sensitivity. AEGIS and GBAR, two experiments designed specifically to measure the gravitational behavior of antimatter, are developing entirely new techniques for producing cold antihydrogen and dropping it in controlled freefall. Each of these experiments attacks the matter-antimatter question from a different angle, and together they form a coordinated assault on CPT symmetry that is unprecedented in the history of physics. Then there is the elephant in the room, or rather the elephant in the tunnel. The Future Circular Collider, known as the FCC, is CERN's proposed next-generation accelerator, a machine so ambitious that it makes the Large Hadron Collider look quaint. The FCC would be a ring roughly 100 kilometers in circumference, more than 3 times the size of the LHC, buried beneath the Geneva countryside and extending into neighbouring France. Its first phase would collide electrons and positrons at enormous energies to produce precise measurements of the Higgs boson and other standard model particles. Its second phase would collide protons at energies of roughly 100 TeV, 7 times higher than the LHC, probing energy scales where new particles and new forces might reveal themselves. The connection to antimatter is indirect but profound. If the alpha anomaly is real and is caused by new physics, whether Lorentz violation, supersymmetry, extra dimensions, or something else entirely, then the particles responsible for that new physics should also show up at high energies if we look hard enough. The FCC would be the machine to find them. It would complete the circle, connecting the low-energy precision measurements of alpha with the high-energy exploration of a frontier collider, each informing and constraining the other. A confirmed CPT violation in antihydrogen would provide a target for the FCC, a specific energy scale or coupling strength to aim for, and a discovery at the FCC would provide a mechanism for the CPT violation, a particle or interaction that explains why the mirror is cracked. Scholars still argue about whether the FCC should be built at all. The estimated cost is roughly 20 billion euros, and the construction timeline extends into the 2040s. Critics argue that the money would be better spent on smaller, more targeted experiments, or on entirely different approaches to fundamental physics. Supporters counter that the history of particle physics is a history of big machines producing big discoveries, and that retreating from the energy frontier would be a surrender that the field cannot afford. The debate is fierce, politically charged, and unlikely to be resolved anytime soon. A confirmed CPT violation from Alpha would be the strongest possible argument in favour of building the FCC, because it would mean there is definitely new physics to find, and the only question is where to look. A historical fact that resonates with this moment is the story of the superconducting supercollider, the SSC, a machine that was being built in Texas in the early 1990s. The SSC would have been even larger than the LHC, with a circumference of 87 kilometers and a proton-proton collision energy of 40 TeV. It was cancelled by the United States Congress in 1993 after cost overruns and political opposition, a decision that shifted the centre of gravity of particle physics from North America to Europe and handed CERN the leadership position it holds today. Many physicists view the SSC cancellation as a cautionary tale about the fragility of big science funding and the importance of public support for fundamental research. Here is a quirky detail about the proposed FCC that engineers find both exciting and terrifying. The tunnel, at 100 kilometers, would pass beneath several towns, a river, and the foothills of the Jura Mountains. The geological survey required to determine whether the rock along the entire route is suitable for tunnelling is itself a major engineering project, involving hundreds of boreholes drilled to depth of several hundred meters. The survey has already revealed that certain sections of the route pass through layers of molasse, a type of soft sedimentary rock that is notoriously difficult to tunnel through. Whether this geological challenge can be overcome at reasonable cost is one of the key technical questions facing the FCC project, and it is a reminder that even the most abstract physics ultimately depends on the most concrete engineering. Beyond the FCC, some visionaries are imagining antimatter experiments in space. In microgravity, free from the seismic noise and gravitational gradients that limit ground-based experiments, antimatter traps could achieve even longer confinement times and even higher precision. The idea of launching a magnetic trap containing antihydrogen into orbit sounds fantastical, but preliminary design studies have been conducted and the concept is not fundamentally impossible. It is merely extraordinarily expensive and technically demanding, which in the world of big physics amounts to a polite way of saying, give us 20 years and a bigger budget. You settle into the thought of antimatter floating in orbit, circling the Earth in silent magnetic suspension, probed by lasers fired from a satellite, while below the planet turns and the people on it sleep. It's a beautiful image, impractical and distant, but no more impractical than the idea of trapping antihydrogen would have seemed 30 years ago. The future has a habit of arriving faster than anyone expects, especially when the universe drops a hint this tantalizing. The machines will be built, or they will not. The data will confirm the anomaly or dissolve it. But beneath the engineering and the statistics, there is a deeper layer to this story, a philosophical one, and it has been quietly gathering weight since the moment you first heard the word symmetry. Because if CPT symmetry is truly broken, the implications extend far beyond particle physics. They reach into the foundations of how we understand reality itself, and they touch questions that scientists and philosophers have been circling for centuries. Symmetry is not just a tool in physics, it is the organizing principle. It is the reason physics works at all. When a physicist says that the laws of nature are symmetric under some transformation, they are saying something extraordinarily powerful. They are saying that the universe does not care about certain things. It does not care where you are, which gives you conservation of momentum. It does not care when you are, which gives you conservation of energy. It does not care which direction you face, which gives you conservation of angular momentum. These connections between symmetries and conservation laws were formalized by the mathematician Emmy Noether in 1918 in what is now called Noether's theorem, and it remains one of the most beautiful and far-reaching results in all of mathematical physics. Every conservation law you have ever encountered, every quantity that physics says cannot be created or destroyed, is the reflection of a symmetry. The universe's indifference is the source of its order. CPT symmetry sits at the very top of this hierarchy. It is the symmetry that says the universe does not care whether you're made of matter or antimatter, whether you're reflected in a mirror, or whether time runs forward or backward, as long as you apply all three transformations simultaneously. It is the ultimate expression of even-handedness, the universe's deepest promise that no version of reality is fundamentally privileged over any other. Breaking CPT does not just remove a line from a textbook, it removes the flaw from beneath the entire structure of symmetry-based reasoning that has guided physics for over a century. And that is philosophically terrifying and exhilarating in equal measure. If CPT is broken, it means the universe does care. It means there is a preferred version of reality, a way things are supposed to be, baked into the laws of physics at the deepest level. Matter is not the same as antimatter. Forward is not the same as backward. The mirror lies. This has implications for determinism, the philosophical position that the future is completely determined by the present state of the universe and the laws of physics. If the laws themselves have a built-in asymmetry, a preference for one direction of time over another, then the arrow of time is not merely a statistical phenomenon arising from entropy. It is fundamental. The universe does not just happen to run forward, it is built to run forward. The past and the future are genuinely, physically different, not because of our limited perspective, but because of the structure of reality itself. Scholars still argue about what this would mean for the concept of beauty in physics. Since at least the time of the ancient Greeks, there has been a deep-seated belief that the fundamental laws of nature should be beautiful, which in practice has meant symmetric. Plato associated the elements with perfect geometric solids. Kepler initially tried to fit the planetary orbits into nested Platonic solids before being forced by data to accept ellipses. Einstein was guided by principles of symmetry and elegance throughout his career, and many of his contemporaries judged physical theories partly on aesthetic grounds. Dirac himself famously declared that it is more important to have beauty in one's equations than to have them fit experiment, a statement that is either profoundly wise or profoundly dangerous depending on your relationship with data. A CPT violation would challenge this aesthetic tradition directly. It would mean that the deepest laws of nature are not perfectly symmetric. They are lopsided, biased, tilted in favour of one outcome over another. Some physicists find this prospect disturbing, a betrayal of the elegance that drew them to the field in the first place. Others find it liberating, a reminder that the universe is under no obligation to conform to human preferences for beauty. Nature is what it is, and if what it is turns out to be slightly asymmetric at the deepest level, then our concept of physical beauty needs to expand rather than contract. Here is a historical fact that brings this philosophical thread into sharp relief. When the physicist Chen-Ning Yang first proposed that parity might be violated in the weak interaction, his colleague Wolfgang Pauli was so appalled by the idea that he reportedly said he could not believe God was a weak left-hander. Pauli's objection was aesthetic, not scientific. He felt that a fundamental asymmetry between left and right was too ugly to be true. He was wrong. nature was indeed left-handed in the weak interaction, and the aesthetic objection, however sincerely felt, counted for nothing against the experimental evidence. The lesson is clear. The universe does not consult our taste, a quirky fringe tidbit to accompany this thought. Some philosophers of physics have drawn a connection between CPT violation and the anthropic principle, the idea that the observed properties of the universe are constrained by the requirement that conscious observers exist to observe them. If CPT symmetry were exact, matter and antimatter would have annihilated completely in the early universe, and no observers would exist. The fact that we are here to ask the question implies that CPT must be violated, at least slightly, or that some other mechanism broke the symmetry. In this view, our existence is not just compatible with a broken mirror, it requires one. You're lying in the dark, a conscious observer made of leftover matter, and your very presence is evidence that the universe's deepest symmetry is imperfect. That thought has a strange vertiginous quality, like looking down into a well and seeing your own reflection looking back up, slightly distorted. The mirror is cracked, and you are the proof, or perhaps you are the reason. Or perhaps the distinction between proof and reason dissolves when you're talking about the foundations of reality at this hour of the night. The well is deep, your reflection shimmers, and somewhere far below the laws of physics hum a tune that is almost, but not quite, perfectly in key. You have come a long way tonight, from the surface of Geneva down into the tunnel, from Dirac's notebook to Anderson's cloud chamber, from Cronin's kaons to Alpha's magnetic bottle. You have watched the universe reveal its mirror, watched physicists test that mirror with increasing precision, and watched the glass develop a crack so fine that only the most delicate instruments on Earth can detect it. The question that remains, the one that will follow you into sleep, is the simplest and the most profound. Why is there something rather than nothing? It is not a new question. Gottfried Wilhelm Leibniz posed it in 1714, and philosophers have been chewing on it ever since. But tonight the question has a different texture, because you now know enough to feel its full weight. The Big Bang produced matter and antimatter in nearly equal quantities. Nearly. Not exactly. That tiny imbalance, 1 part in a billion, is the reason stars exist, the reason planets form, the reason liquid water collects in rocky basins and amino acids fold into proteins and neurons fire in patterns complex enough to wonder about their own origins. You are the residue of an asymmetry so slight that it barely registers in the equations, and yet here you are, warm and breathing, aware of yourself and the darkness around you. The Alpha experiment may have caught a glimpse of why. The spectral anomaly in antihydrogen, that subtle asymmetry in the wings of a spectral line, is not an answer in itself. It is a fingerprint, a trace left by whatever process tipped the scales in the first fraction of a second after the Big Bang. If the anomaly holds, if it survives the scrutiny of further measurements and the skepticism of a community trained to doubt, it will be the first direct evidence that matter and antimatter are not perfect mirror images, that their internal structure differs in some way that the standard model does not predict, that the universe, at its very foundation, has a preference, a lean, a whisper of bias that made everything possible. Scholars still argue about whether such a preference diminishes the universe or ennobles it. A perfectly symmetric cosmos would have a cold, mathematical beauty, the beauty of a crystal or a theorem, complete and self-contained. A slightly asymmetric cosmos is messier, less elegant by traditional standards, but infinitely more fertile. It is the imperfection that allows complexity, the crack that lets the light in, to borrow a phrase from a poet who probably was not thinking about particle physics but captured the idea perfectly. Without that crack, the universe would be a uniform bath of radiation, perfect and sterile, a masterpiece that no one would ever see because no one would exist to look at it. There is something comforting in that thought, something that pairs well with the heaviness of your eyelids and the softness of the pillow beneath your head. You're not an accident, or rather, you are, but you are the most beautiful kind of accident, the kind that arises from a slight imperfection in an otherwise orderly system. A fringe idea that a few cosmologists entertain is that the asymmetry might not be fixed. It might vary across the cosmos, stronger in some regions, weaker in others, producing pockets of matter and pockets of antimatter scattered across distances so vast that they will never interact. If that is true, then the universe is not just imperfect. It is variously imperfect, a patchwork of asymmetries, each one giving rise to its own islands of complexity. You happen to live on one of those islands, made of one flavour of imperfection, looking up at the sky and wondering if there are others. Remember the trap, the magnetic bottle the size of a thermos, floating in a vacuum colder than deep space. Remember the 20 atoms of antihydrogen drifting in that bottle, each one a tiny mirror held up to the laws of physics. Remember the laser, thin as a thread, precise to 13 decimal places, reading the antiatom's secrets one photon at a time. Remember the postdoc on the night shift, watching the histogram build on the screen, sipping cold coffee, wondering if the blip is real. Remember the spider in the laser enclosure. The spider is fine. That is the image to carry with you. Not the grand machinery of the collider or the sweeping abstractions of theoretical physics, but a small room underground, a handful of atoms that should not exist, and a group of humans patient enough to ask them questions. The answer, when it comes, may reshape our understanding of the universe, or it may not. Either way, the asking is what matters. The willingness to sit in the dark and listen for something impossibly faint, something that might not even be there, is the most human impulse imaginable. It is the same impulse that makes you lie here at this hour, listening to a story about particles and symmetries, not because you need the information, but because you want to feel the wonder of it. And now the wonder softens. The edges of the story blur, the way a landscape blurs when the light fades. You do not need to hold on to the details. They will be there in the morning if you want them. The sigma levels and the spectral lines and the names of experiments can wait. What stays with you now is simpler. The universe had a choice, in its first moments, between perfect balance and glorious imbalance. It chose imbalance. It chose complexity. It chose, in some sense that physics cannot yet fully articulate, you. The magnets hum, the atoms drift, the laser whispers, and the biggest unanswered question in physics, the question of why there is something rather than nothing, settles over you like a second blanket, not heavy but warm, not urgent but present. You do not need to solve it tonight. Nobody does. It will keep. It has kept for 13.8 billion years. It can keep for one more night. Your breathing slows. The tunnel is quiet. The antihydrogen floats in its magnetic cradle, patient and silent, holding a secret in its spectral lines that the universe has guarded since the beginning of time. Maybe tomorrow the data will speak, maybe next year, maybe a decade from now, when a machine that has not yet been built reads a signal that has not yet been imagined. But tonight, the secret is safe, tucked into the wings of a spectral line, waiting for someone to ask the right question in the right way at the right time. The lights in the laboratory dim one by one, though of course they do not really, because the night shift never ends at CERN. But in your mind they dim. The hum fades to a murmur, the murmur to a breath, the breath to a silence that is not quite silence but something gentler, the sound of a universe that is still figuring itself out, still leaning slightly to one side, still becoming. You are part of that becoming. You always have been. 1 billion years from now, the atoms that make up your body will be scattered across the cosmos, recycled into stars and dust, and perhaps, if the asymmetry holds, into new islands of complexity that cannot yet be named. But for now, they are here, arranged into the shape of you, warm and quiet and wonderfully, improbably real. Sleep well. The universe will still be lopsided in the morning, and that, when you think about it, is the most comforting thought of all.